Okay, hi, good evening, everyone. My name is Chetan Singh Chauhan. I'm the secretary of Kaziranga House, and I welcome all of you to this last session of this week long revision series that we planned and organized at Kaziranga House. This is the last session. This is the machine learning techniques end term revision session. I hope you find this useful. And we have invited the current MLPTA, Pulkit Mangal, who's also the previous MLTTA. And he's very graciously accepted that invitation for this particular session. And yeah, so this is the last session before you appear for your end term tomorrow. I wish you all the very best for your end term tomorrow, and I hope you find this session useful. Before Pulkit takes over, I have a small request to all of you that please make the session a little more interactive. Pulkit is a veteran TA. He has been a TA since May 2023. Um, I often joke about it that this guy will get a pension from IITM. But yeah, please make the session a little interactive so that he doesn't get bored and you guys don't get bored. If he asks you any questions, do respond to those questions. If you have any questions, do ask him those questions as well. If you have not prepared at all, be blunt. Tomorrow is your end term. You do not have the liberty of being hesitant right now. So be blunt about your preparation. You don't know any concept, be shameless in saying that I don't know this concept. Please explain it to me from scratch. And I hope that this session somehow helps you in your end term preparation if you have not already prepared for your end term. So yeah, Pulkit, are you here?
Yes, Chetan. Am I audible?
Okay. Yeah, perfectly audible. You may take over now. And yeah, thank you for accepting the invitation.
Yeah. Thank you, Chetan, for such a nice intro. Without any further delay, let's start the session now. I'll start sharing my screen.
Good evening, sir.
Good evening. Yeah. So, my main plan for today is to cover the last 4 weeks in detail. Uh, but first, I will start with the quick intro of what was happening in the last 8 weeks that we've seen so far. Okay, so we'll start first from that part, and we will look at week 9 to 12 in the more details. So, uh, week 1, if I start, in the week 1 to 4 part, we basically saw the unsupervised learning part, in which week 1 we saw the PCA. For week 2, we moved to the kernel version of our PCA, that is kernel PCA, for capturing the non-linear relationship part. For week 3, we had the clustering algorithm, K-means. And for week 4, uh, we had estimation and GMM and EM algorithm. So these 4 weeks covered our unsupervised learning part. Like if you have just given the data, then what type of patterns and any kind of relationship that you can find from the given data. That comes for the unsupervised learning task, which does not involve any kind of label prediction. Then we start off with supervised learning from week 5 to 12, in which week 5 and 6, week 5 and 6, we saw the regression part, starting with the simple linear regression, followed by the gradient descent method, and then the kernel version as usual. For week 6, we move ahead a little bit in more complexity for the regression and introduce the Rizz and Lasso regression. Along with the cross-validation methods. From week 7, we move on to classification problems, and in which we first started with the k neighbor, and decision tree. In week 8, we had the generative type of algorithm, in which the only generative algorithm that we saw in our course was the naive base, in which the more detailed explanation for generative algorithm was regarding the naive base, in which it includes the binary features. We saw a little bit on linear discriminant analysis also, which basically the extended version of our simpler naive base, in which not having the binary feature, we also included the features having following the normal distribution. Then week 9, we started with the perceptron and the logistic regression. So even though the term suggests it's a regression method, but it is used for classification purpose. Week 10, we move on to the SVM and the kernel version of SVM also. With respect to hard margin, uh, we'll look this thing in detail in some more time. Week 11, we had the soft margin SVM. Then we have bias variance trade-off. Then we have ensemble method. So in the ensemble methods, we random forest, bagging, and ADA boost. And we concluded week 12 with some summary of all the classifications method that we saw and the different type of loss function for these classification problem. And an intro to artificial neural network. So this was the whole syllabus of MLT. Now from week 1 to 8, I will give a quick recap of all the algorithms that we have seen. Then from week 9 to 12, I will give a detailed explanation of these algorithms. Along with, we have some questions from week 9 to 12 that we are going to solve today. Except that if you have any question from your end, I will take that question also. Okay. So yes. Okay.
No, sir.
So week 1, the main algorithm that we saw was the PCA. Okay. So what does basically PCA do? PCA helps you try to find a low level dimensional representation for your high dimensional data. Okay. Representation. But the main important thing that PCA assumes that your data set has a linear relationship. Okay. So if geometrically we saw, then if you have your data points somewhere around here, suppose now even though your data points lying in a 2D coordinate system, okay, but most of the data points are lying along across one line, so you can represent this entire data set using this line only. Okay, so this is what it is mean by a low dimensional representation for your high dimensional data. This was just a small example. But in general, when you have very high number of features like 100 or 50, then this can be very useful in that time to reduce the dimensionality for your data set. Okay. Now let's list down the steps that we need to implement the PCA. Now, what is the first step that we do while doing the PCA?
We find mean of the data set.
Yeah, so mean of data points. Okay. Let me tell one more thing that in the MLT, the notations that we were following was that all of your data points are stacked column wise. Okay. So the matrix of your data set that you are going to get will be a D cross N matrix, where D represents the number of features and represents the number of data points. Okay. So your first data point would be your first column in the matrix, second data point would be your second column in the matrix, and so on. And thus it will be a D cross N matrix. Each xi will be of RD. So what will be the mean? How you will represent the mean of this data matrix? You are going to sum all the data points x1, x2, x3 till xn divided by n. Okay, that will be the mean data point. Okay. So once you find the mean, what will be the next step?
Subtract it from that
Yeah,
x.
very good. So for each data point that you have, you will subtract this mean vector that you got. Okay. So you'll subtract the mean vector from each data point. Okay. Then what will be the next step?
Finding covariance matrix.
Finding covariance matrix. How you find it?
1 by n x into x prime.
Okay. Where this X is a matrix, which is the center dataset matrix. Okay. So that is basically all these data points will be the centered. Okay. That the centered means the mean will be subtracted from each of these data points, and that dataset matrix will be used for finding the covariance matrix. Okay. Once you find the covariance matrix, what will be the next step?
Eigenvector and eigenvalue of the matrix.
Eigenvalue and eigenvector for covariance matrix. Now, what does this eigenvalue represent?
Variances in the data set.
Variance along the direction of, so any ith eigenvalue represents the variance along the direction of ith eigenvector. Corresponding eigenvector. Okay. So if we have eigenvalues, suppose lambda 1, lambda 2 till lambda, so how many eigenvalues it can have? A covariance matrix.
Sir, could you please repeat the question?
How many eigenvalues can your covariance matrix have? Less
At
than
max
three?
D.
Yes, correct.
Depends on this.
D is the correct, and it can have D eigenvalues. Okay. Now, few of the properties of the covariance matrix, that it is a positive semi-definite matrix. What does it mean by positive semi-definite matrix?
Eigenvalues would be greater than equal to 0.
Okay, it's a symmetric matrix also. Positive semi-definite means all the eigenvalues that you are going to get would be greater than equal to 0. Okay, and you will get d eigenvalues, and corresponding you will be getting uh, d eigenvectors also. Okay, so all these eigenvalues represents the variance along the direction of these eigenvector. That is, if you are going to just take these eigenvectors and project your data points along the direction of these eigenvectors, then the variance that you are going to get for that data set representation of the projected data set will be the eigenvalues. Okay. Now, how we do the projection? How you do the projection of your data points along the direction of these eigenvectors?
Sir, one thing, sir.
Hmm.
Sir, I am telling that eigenvalue would be equal to the number of row.
Number of row, yes, that would is correct. For the X matrix, if you are saying, yes, because that
Actually,
is,
yeah. So
yeah, X even if for the C also it will be correct.
suppose is if any matrix has three row and two columns, so
Hmm.
eigenvalue, how many eigenvalue will be there?
See, eigen decomposition is only for the symmetric, oh, sorry, not the symmetric, square matrix.
Yeah, so whenever we are dealing with square eigenvalue, so we can say whether it is D, whether it is N, isn't it? There is no
Uh,
boundary for this
no, no,
because
see,
this is
first
square.
thing, that eigen decomposition, that is finding the eigenvalues and eigen vectors, is only for the square matrix. Because how you find the vector or eigenvalues is basically you will having the matrix A, or it's just a notation, you can take any matrix, okay? Then minus lambda times I, and you will be basically calculating the determinant of this matrix and setting that to 0 to calculate for the eigenvalues, right?
Yes, sir. Yeah, this is the
Okay. So,
formula for
hmm,
finding.
yeah. And that's why if you notice that the lambda times I, this will be a square matrix, right?
Yes, sir.
Okay. So A also has to be a square matrix. And another thing, that determinant only exists for the square matrix. So eigen decomposition is only for the square matrix. That's why the first thing that you said was the wrong, that for a matrix 3 cross 2, we cannot do the eigen decomposition. Now coming to the second part, about how many eigenvalues it will have. Okay. Now here, because we have a specific case that it is a positive semi-definite matrix, okay, we know that it's all of the eigenvalues that it is going to get would be greater than or equal to 0, right?
Yes, sir.
Okay. Now it can happen that it can have like multiple eigenvalues which are 0. So if you care about the unique eigenvalues, then that can be less than d. Okay. But in the, total, you will be going to get d eigenvalues. Okay. It can happen that the number of zeros that you are going to get, that can be like more than 1. So if you care about the unique eigenvalues, that can be less than d. But the total number of eigenvalues that you are going to get would be d only. Okay. Nice.
Okay, sir.
Yeah. So I hope it is all right for all of you also. So let's talk about the main part, that is the projection of my data points along the direction of these eigenvectors. We care about these directions because the lambda 1 here, that is supposed to be the largest eigenvalue. Okay. Eigenvalue. Okay. This represents the highest variance. Okay. In the direction of the W1, that is the first principal component. Okay. Now, variance is basically, you can see as the amount of information you are capturing. Okay. So if you are just going to project your entire data set along the direction of W1. Okay, then you will be getting some variance, and that variance will be higher than if you're going to project your data points along either W2 or W3 or some other eigenvectors except the W1. Okay, because lambda1, that is its corresponding eigenvalue, will be highest here. So that's the first thing, that all of these eigenvalues, we will be arranging them in descending order. Okay, now if you want only one dimensional representation, then you can only take the single eigenvector. If you want a two-dimensional representation, you can project your entire dataset along the direction of the vector space or subspace spanned by these two eigenvector W1 and W2. Okay, so all of these eigenvectors that you are going to get here, okay, will be orthogonal, and sorry for the term, it should be orthonormal. Okay, can anybody explain what does it mean by orthonormal? Yes, Hariom. Okay, I think it was a mistake. So my question was, can anybody explain what does it mean by orthonormal?
Yeah, the dot product of each others are going to be 0.
Yes, and that was the case for orthogonal.
Normal,
Oh,
norm is 1.
norm
Norm
is
is
1.
good. Yeah. So the dot product between any of the pairs of these vectors would be 0, and the norm of each of these vectors would be 1. So that's what it does it mean by orthonormal. Okay. And if two vectors are orthonormal, then they would be independent also, because the angle between them would be 90. So they are both going to represent different directions. Okay. So they would be linearly independent also. Okay.
Sir, what is the difference between orthogonal and orthonormal?
Orthogonal only say that your vectors, the pairwise dot product between any two vectors would be 0, but it doesn't enforce that the norm of your vectors would be 1. Okay. While orthonormal say that it is orthogonal also, but the norm of each of these vectors would be 1 also. Okay. Like for any orthogonal set, you can make it orthonormal by just dividing by the norm of each of these vectors. Okay. Yeah. So let's come to the projection part. How you do the projection? If I want to project my data points across the direction of each of these W. Okay. So we have to, for any ith data point, we will be taking the dot product with respect to the eigenvector on which we are going to project. So if I am going to project along the direction of W1, I will be taking the dot product with respect to W1. Okay. Now this is called the scalar projection. Okay. If you are just doing the dot product, just dot product means it's the scalar projection. Okay. So as the term says, it's the scalar projection. That is because the value that you will be going to get here would be just a scalar number. Dot product always returns a scalar value, just a real number. Okay. But if you want to do the full projection, then that would be xi transpose W1, and you will be going to multiply this scalar quantity with the vector on which you are projecting. So I am projecting here on W1. So that's why I'm going to multiply this scalar quantity with respect to W1 also. Okay. So that's what it is called as the full projection. Okay. Now this is for one eigenvector projection. We can extend this idea to project onto multiple eigenvectors, such as if I want to project on W1, if I want to project on the subspace spanned by W1 and W2, that is, I want a two-dimensional representation, then I can do it in this way. Xi transpose W1 times W1 plus Xi transpose W2 times W2. Okay, I will just add these two quantity. Now we can extend this further on. If I want to do it three-dimensional representation, just I can add one more quantity here, and I will get three-dimensional representation. Okay, and let's
Yes, sir.
denote.
Sir, one thing,
Hmm,
sir, this X transpose W
hmm,
uh, into W.
hmm.
I have seen also this divided by W norm or W norm
Yeah.
square. What was that?
So in our course, we are taking this assumption that the eigenvectors that we are getting are orthonormal. That's why I name them here that they are orthonormal. Okay. In general, if you are going to do the projection, the formula for projection for a vector onto another vector is okay. In general, let's say if you have a vector u and you are projecting it on vector v, then that projection is given by u transpose v times v divided by v transpose v. Okay. So because we are taking this assumption that our eigenvectors are orthonormal, that is the norm of each of these vector would be 1. The v transpose v here, or specifically for this case, it would be w1 transpose w1 would be just 1, right? So that's why I have not included the denominator part. Okay. But if your eigenvectors that is given to you in the question are not orthonormal, then either you can take the normalized one, or you can add this quantity v transpose v in the denominator for each of these quantity. Specifically w1 transpose w1, here w2 transpose w2, and thus you will be getting the projected data point. Okay, so that's what main thing was there in the week 1.
Hello, sir.
Yes.
Yeah, could you please explain the concept of residue?
Okay, residue. Yeah, so see, once we do the projection, what we will be getting is an approximate representation of your original data point. So of course it has lost some information because we are not making use of all the directions. All the direction, by that I mean all these eigenvectors, we are not using them. If you are going to use all these eigenvectors for the final representation, that is if I go till WD, then I will get my original X back. But because here we are doing only a only using of two eigenvectors, so I am of course going to lose some kind of information. Okay, so that is captured in the residue, and that you can get is from xi. That was my original data point. You can subtract the projected one. Okay, I'm representing my projected data point as x tilde. Okay, so for any as data point, we can subtract its projected one and take the norm square. Okay, norm square means x transpose x. Okay, that is also the norm square of x. So it would be just xi minus xi tilde transpose xi minus xi tilde tran. Okay, so norm square is basically the dot product between the vectors. Okay, so you will be getting one vector when you do the subtraction of these two vectors. If you take the dot product of that vector with itself, that is basically the norm square. Okay,
Okay, sir.
so that's the residue part. Now you can divide it by n also if you want to do the residue for all the data points and average residue if you want to find. And you can just sum across for all the data point and divide it by n number of data points. So you will get the average residue. Okay, so let me add it as. Any more doubt, anyone?
I have one doubt, sir.
Yes.
So, the main goal for PCA is dimensionality reduction.
Yes.
So, can you quickly explain the steps for PCA? How is it reaching to the goal? Like we are
Okay.
first calculating mean,
Yeah.
then covariance matrix, and other steps.
Yeah. So we have subtracted the mean. We have calculated the covariance matrix. Okay. Then we have captured the eigenvalue and eigenvector. Now what we are doing is we are projecting our data point across the direction of these eigenvectors, okay, which if you order them in the terms of their information capture power, then W1 captures the most information, W2 would be capturing less information than W1, and so on. Okay, and now we are projecting our data point along these eigenvectors, and then based on the number of eigenvectors you are going to select, that would be your new dimension for your data points. Okay, but that dimensionality reduction is only captured if you just consider the scalar projection part. Okay, because if you notice, if you are going to do the full projection, then technically the space in which your data point will lie will be the same space. So if you're not able to understand what I'm saying, that can you first tell me what will be the dimension of each of these eigenvectors? Like in what space will they lie? In what space my each of these eigenvector will lie? R, D, R, and
Guys, even if you don't know the answer, just say it. Just make the
Yeah,
session a little
actually,
more
I
interactive.
have quite forgotten eigenvector and eigenvalue. I just remembered how to calculate those things, and
yeah. So do you remember the eigen equation that
yeah,
V AV is equal to
yeah,
lambda V, right?
lambda v, right? Yeah,
So where V was the eigenvector, lambda was the eigenvalue. Okay.
eigenvalue.
Now suppose if your yes, so RMN has already given the answer. As I said here that you do the eigen decomposition only for the square matrix. So let's suppose A is my covariance matrix, then it will be of order D cross D. Okay. And I am multiplying it a vector. So to make this product successful, what should be the dimension of my this V vector here? If I'm multiplying it with a D cross D matrix, and what should be the dimension of this V so that this matrix product will be successful?
D.
D cross 1, right?
Yeah.
Okay. So each of these eigenvectors will have the dimension D cross 1.
Okay.
Okay. This is the first thing. Now here we are taking a scalar projection. We are multiplying it with a D cross 1 eigenvector. Okay. So the final output that you will be getting from here would also be a D cross 1 vector, right?
Yeah.
Okay. This will be a scalar quantity. This is a vector in RD. Okay. And this is some scalar quantity. So the final output will be in RD. Similarly for this will be also in RD. Okay. So if you are going to add two vectors in RD, you will be again getting a vector in RD itself.
RD.
Okay.
Yeah.
Now, if you notice that our vector initially was also in RD, that's what we assumed here, that your
Yes.
vectors are in RD. So you might be thinking that technically we are not reducing anything in terms of dimension. Yeah.
Mm.
Now, but that is just that the space in which your data point will be lying will be in RD. Okay. So let me take a example that what will be happening that when you are going to do the full projection with uh, two eigenvectors, suppose your vectors, okay, original data points lie in R3. Okay, so there would be some data points here. Okay, this is a vector in R3. Now, if you're going to project this vector, okay, using the uh, eigenvectors, first two eigenvectors, okay, then the projected vector will also lie in R3, but it will lie in a two-dimensional subspace of this three-dimensional vector space. So two-dimensional subspace can be a plane in R3. Okay. So any coordinate of the plane, so it can be a plane in R3. Okay. Where this data point is getting projected. Okay. So this is how you're going to reduce the dimension here. Okay. So first it was in R3, but now it will lie in a two-dimensional plane inside your three-dimensional space. Okay. Is it clear?
Yeah. Yeah.
Okay. Now, this was the case if you're going with the full projection. In terms of the values that it will contain, that is the space in which your data point will be lying, it will still be in R3 because it will have all the three coordinates values. Okay, but it will lie in a smaller or low dimensional subspace. Okay. Now, if you want to reduce it in terms of dimension also, that is from, let's say, this R3, I want to go with a representation in R2. Okay, then you only take the scalar projection. Okay, and then how you represent it? It's basically your x tilde would be, the first coordinate would be x1 transpose w1, second coordinate would be x1 transpose w2. Okay, that is whatever the scalar value that you are getting. Okay, you'll stack them in a vector. So first one would be the first coordinate. With respect to second scalar projection, that would be the second coordinate value. So now this will be in R2 because it has only two values in the vector, right? Okay. So
Yeah.
if you're going with the full projection, your original vector will still lie in the same space in which it was already, but now it will lie in a lower dimensional subspace. Okay. But if you are going with the scalar projection, then you can actually reduce the dimension also by just taking the scalar values with respect to each eigenvalue, eigenvector projection. Okay.
Yeah.
Yeah. Sure, sure. I will go a little bit quick now because we have so many weeks to cover. So let's go with the week 2. So in week 2, the main concept that we introduced was the kernel. Okay. So can anybody tell me the need for the kernel? Why we introduced it? What does it do?
There was issues with PC.
Sorry.
There was some issues related to doing the PC.
Okay, I was not able to hear you properly, but
Due to time complexity.
yeah, time complexity. Okay, when we use then data is not linearly separable. See, linearly separability. This thing actually came when we go with the supervised learning task. I think what you meant to say was when your dataset does not have a linear relationship.
Yes,
Okay.
yes, sir.
Yes, sir. If dataset is not linear,
Uh,
then we use
Linear
kernel.
relation. Yeah, that is basically if it's your dataset is something like it,
Higher degree polynomials,
yeah,
no?
it's kind of like, let's say it have this circular relationship. Okay, so all your data points are lying across this boundary of circle. Okay, then what will happen that if you're going with the, let's say using only one eigenvector, if you're going to do the representation, and if you choose any direction, you will be only going to get the same kind of variance. You are not actually storing more information. Okay, so to overcome this, that when your dataset has a non-linear relationship, we introduce this kernel. So what does kernel do? It captures the relationship between your data points into the higher dimension. And one assumption that we here make that when we project my data points into some higher dimension, they will be having linear relationship. Now, the reason you can think of them is as you move to some high dimensional space, the sparsity increases. That each of your data points, okay, will become distance to each for each of your features will become distance to each other. Okay, so as the sparsity increases in the high dimensional space, they will become linear to each other. Okay, even if you don't understand this part, you can for now just remember that uh, kernel captures the relationship between two data points in the high dimensional space. Okay, so for any valid kernel, okay, the kernel function is defined as the phi of x transpose phi of y, where phi is the transformation that project my data point x into high dimensional space. Okay, mainly we saw two types of kernel function in our course. One was the polynomial kernel, other was the RBF kernel or Gaussian kernel. Okay. So polynomial kernel. Can anybody tell me the formula for the polynomial kernel?
Sir, is it
Yeah, so xi transpose x, like x transpose x1 transpose x2 plus 1, and whole to the
Mm,
degree anything.
power p. Okay.
Yeah.
So for basically any two data point x1 and x2, polynomial kernel is 1 plus the dot product between these two, x1 transpose x2, and you will make it the power of p. P here is basically whatever the polynomial degree transformation you want to do, that is the value of p. Okay. Now, if you're going with a polynomial kernel, then given the dimension, given the current dimension of my vector, and if I give you the how much polynomial degree transformation I want to do, can you tell me what will be the dimension of the transform space using these two information? That if I give you the d, that is in what dimension my uh, data points like currently, and if I give you p, that is the d plus p, will it be just t plus p? So using these two values, that is the current dimension and the polynomial degree, what will be the value of that, or what will be the dimension of the transform space? P is basically the degree by which you are transforming. So if you have your data point, let's say x1, which is like just an R2, x1, x2, it has two values. Let me take it here like 1 and 2. Okay, so currently this data point line R2. And if I want to do a 2-degree transformation of this, so let me represent this first as F1, this is F2. This is my feature 1 value, this is my feature 2 value. So how I can do the 2-degree transformation is, first part, when my features has 0 degree. So if your features will have 0 degree, it will be just 1, because any number, if you set the power 0, it will be 1. Then you'll be adding the part where your features have degree 1. So F1 power 1, F2 power 2, it's just F1 and F2. Then because you are going it till 2 degree, so now you will be adding the features which will have at least 2 degree. So you can add F1 square, you can add F2 square, and you can add a feature that is the product of these two, F1 into F2. Okay, because this term will also have degree 2. Okay, so this is the P, a 2-degree transformation of my current vector. Okay, if in terms of numerical you want to see, for this given vector 1 2, it would be just 1. Okay, now this one is coming from here, then one more one, that is this feature value, then 2, then 1 square 1, 2 square 4, then the interaction part 1 into 2 2. Okay, the order need not to be the same. Okay, in general, if they will going with the order, then it will be given. Okay, so this is a 2-degree that you will be going at max till 2-degree transformation. Now you can similarly extend this idea to 3, where you can include like f1 cube, f2 cube, f1 square times f2, like that. Okay, so that's what your p here represents. Yeah. So okay, so I was how you calculate the transform space dimension. It's basically d plus p choose p. Okay. So whether you write it as d plus p choose p, this should be equal to d plus p choose d. Okay, because both will be the same value here. So using this formula, you can calculate the transform space dimension. Is it clear?
Yes, sir.
So next we have the RBF kernel also. Okay, that was the exponential of negative x minus y norm square by 2 gamma square Okay. So where this gamma would be given to you in the question if they are going to ask. Okay. The above term represents the norm square of x minus y, where x and y are the data points for which you are going to calculate the kernel value. Okay. RBF kernel, also known as the Gaussian kernel. Okay. So these are the formula that you have to remember.
Sir, what is the full form of RBI?
Radial basis function. Okay. It's not
Okay,
that
sir.
much important. So we have already 1 hour, so we have to move a little bit fast now. In week 2, the next thing was how you implement the kernel PCA. Okay. So see, now what will happen while doing the kernel PCA, that when we were calculating the covariance matrix in our simple or vanilla PCA, we were calculating the covariance matrix in terms of XX transpose, which were returning a matrix of D cross D. Okay. But while in the kernel PCA, we calculate the covariance matrix or the eigenvalue or eigenvector for the matrix X transpose X. Okay, which will be of matrix of order n cross n. Okay, and there's a relationship between the eigenvalue and eigenvector for X transpose X matrix and XX transpose X. So can you tell me what will be the relation? First of all, about the eigenvalue. Will all the eigenvalue for these two matrices will be same? Or only few of them?
No, no, no.
Not all.
Not all, right? Okay, this just remember this, that all, not all eigenvalue will be same, only the non-zero eigenvalues will be the same. Okay, all non-zero eigenvalue of XX transpose and X transpose X will be same. Okay, and if I'm telling that if V is an eigenvector of X transpose X, then XV by square root of okay, I should write lambda comma V is an eigenpair of X transpose X, then XV by square root of lambda. Here also lambda comma will be eigenpair of XX transpose. Okay. So as we are taking that all the non-zero eigenvalue will be same. Suppose lambda is something that is greater than 0. Okay. Lambda is greater than 0. Then for an eigenpair of lambda comma V for the X transpose X matrix, the eigenpair of XX transpose matrix would be lambda comma XV by square root of lambda. Okay. So instead of going with the computation of the covariance matrix using XX transpose matrix, we go with and compute the eigenvalue and eigenvector for X transpose X matrix. Because remember, while calculating the kernel function, we defined our kernel function as the dot product of the data points in the transformed space. Okay. So as this matrix also does the same. Okay. So that's why we can represent that the phi of X transpose phi of X. That is, once you project your data points into the higher dimensional space and then take the dot product, this will be your matrix K. Okay, that is also called as the gram matrix, where each value in this matrix, okay, it will represent the kernel function value between the data points. Okay, so your phi of X transpose will be like phi of X1 transpose, phi of X2 transpose, and so on. And here it would be phi of X1 till phi of Xn. Okay, so once you do the dot product here, so the matrix multiplication, this would be phi of X1 transpose phi of X1. That would be the first value, that is same as the kernel function value between X1 and X1. Then phi of X1, phi of X2. So kernel function value between X1 and X2 and so on. So that's how your kernel matrix is going to fill. Okay. So we'll be using this kernel function this kernel matrix, and find the eigenvalue and eigenvector for this kernel matrix. And using this relationship between the eigenvectors and eigenvalue, we are going to project our data points. Okay. So we know that if okay, is it all right for all of us? Yes, we want to start with the week 8.
No, sir. Go with week 5 to week 8. I have a lot of problems between the week 5 to week 8.
Okay. Yeah, so let
Yes.
me just then finish this part, then I will move
Mhm.
to that. Yeah, so I was telling that instead of going with the calculation of uh, eigenpair for XX transpose, we go ahead and calculate the eigenvectors and eigenvalue for our matrix K, which is the phi x transpose phi x matrix. And using this relationship, we can calculate the eigenvalue and eigenvector for my XX transpose, or here it would be phi x transpose. Okay. So yeah, if you all agree, then we move to week 5. Uh, week 5, we had the linear regression. So again, you will be having matrix x1 till xn, each of them lying in RD. We have n data point x1 till xn. So linear regression can be done in two ways as per our course. One we have is using the normal equation method. Another is the iterative method. Okay. So using the normal equation, how you do the or find the coefficients. What is the normal equation?
Is that X transpose X?
Hmm.
That one?
Yeah,
Yeah,
XX transpose pseudo inverse. So
inverse
if the matrix is invertible,
X.
it's first inverse. X. Okay. This is
X
called
into
as
Y.
your this is called as your uh, normal equation. Okay. You will use this to find the W. Then for the prediction, what you calculate is X transpose W. Okay. And that will give you the predicted Y hat. Okay. And you can calculate the either MSE or some square error using 1 by n norm square of Y minus Y hat. Okay. Both Y and Y hat here are the vectors, because what you will be getting from this matrix vector product would be a vector. Okay. Yeah. So this was when the iterative normal equation way. The second method is the iterative way. So can you tell how we do with the iterative way? It's basically a gradient descent. Okay. So how you perform the gradient descent is, you will start and initialize your weight vector that you have. Okay. With let's say 0. If nothing is given, I'm assuming here that my data points lie in R2, so that's why I've taken it to 0. But if your data points lie in R3, then 3 0 like that. Okay. So you can start with the 0 0. If something else is given in the question, you will start your initializing of your weight vector with that vector. Okay. So after initialization, we have to calculate the gradient of my loss function with respect to W. Okay. So the gradient that comes out loss function with respect to W, what it will be? What will be the gradient of my loss function with respect to W?
2x transpose x into w minus 2xy.
X transpose w minus xy. Okay, we can take the two common. Okay, so this will be the gradient value. And to update my initialized weight vector, we use this following update rule that wt plus 1 is wt minus eta times the gradient of the w with respect to loss function. Okay, t here denotes the timestamp. So as here I am writing 0, that is the 0's timestamp, that is the time where we are initializing my weight vector. And if I'm going to update this, then I will call it as w1. I will use w naught here. Then eta denotes the learning rate. Okay, and this quantity gradient. Okay, 2 times xx transpose w minus xy. The w that we are going to use it here would be this w here. Okay, so it would be w naught. Okay, and using that we will be getting w1. Okay, then again we can go with and use this w1 to obtain w2. So this is an iterative manner. Okay, using the previous information we are finding the next information, and this cycle will keep on running. So this is an iterative way to find your optimal weight vector for your linear regression problem. Okay, now what is the problem with this vanilla gradient descent?
Sir, if n will be large, then there will be problem.
Yes, because first it involves this calculation of xx transpose. This matrix calculation each time will be quite heavy. Okay, so as the number of data points increases, the calculating gradient descent using this vanilla way, okay, will be computationally heavy. So we move with what is something called as the stochastic gradient descent. Okay, so how we perform the SGD? What is the main difference between a vanilla gradient descent version and the stochastic gradient descent version?
We take subset, I think, from whole space.
Yeah. So instead of taking all the data points to find the gradient, so as here the matrix that we have xx transpose, it has all the data points. Okay, so instead of taking all the data points, we take a subset of the data points. Okay, so let's suppose you are only taking the initial 5 data points. Okay, it is not necessary that you will go from the start. You can randomly select a subset. Okay, so just a random subset you are going to select, and using that subset only, you are going to do this gradient calculation. Okay, so let's suppose I have this matrix x1, x2, 3, 4, 5, 6. Okay, so I have 6 data points. Let's suppose I will first take 3. So first 3. Okay, then I will call this x dash matrix, which has just x1, x2, and x3. Then I will update my weight vector w1 using w naught minus eta times 2 into x dash transpose w naught minus x dash y. Now y dash here also, because you are only going to take the label of these 3 data points. So I will get from one weight vector. Then I can take the remaining 3 data points. Okay, and using that also I will going to get some other weight vector. Okay, minus eta times 2. Now here we'll be taking these 3 data points to calculate the gradient. Okay, and this will keep on going for some number of iteration. And in the end, what we'll be doing is we'll be taking the average of these uh, weight vector that we are going to get at each iteration. Okay, so that's how the SGD works. Okay, so let me repeat it again. What you do is instead of taking all the data points, we take a subset of the data point to update the weight vector. And in the end, we'll be just doing the average of all the weight vectors that we have got, because the reason behind this, as we are not taking the entire data set to do the gradient descent update, there will be variance between the updates of the weight vector that is going to happen. Okay, so it's going to oscillate a little bit. So to reduce that variance, we take the average in the end. Okay, So that's the SGD rule. Now, any doubt in the SGD part? Okay.
So what is y
No,
dash?
sir.
Sorry.
So what is y dash?
Yeah, why this? So as we are only taking 3 data points here, so you are only going to get take the label of these 3 data points only. So that's the y dash. Okay.
Okay, sir.
Any more doubts?
No, sir.
So next is kernel regression. Okay. So uh, I will be just writing the main equation of the kernel regression. Okay. That you are going to obtain your W star as phi of x times alpha. Okay. Where this alpha is K inverse y. K is again your gram matrix for the kernel matrix. Okay. That is the phi of x transpose phi of x. Y is your label vector. Okay. Generally, the question that is given in the kernel regression question is uh, going to ask for the prediction for a test data point, in which what they are going to do is they will give you a X test data point, okay, for which you have to do the prediction. They will give you alpha. If they are not going to give you alpha, they are going to give you the data point, and you can find the alpha using this equation K inverse Y. You are going to find the kernel matrix. You will be having the label using which you can find your alpha vector. Alpha will be a vector here because K is a matrix, Y is a vector. Okay. Once you find alpha, what you are going to get is the W star form, that is phi of x alpha. But because we do not know the explicit transformation form of phi, and what we only care about is the prediction part, we do the prediction as W star transpose x test. Okay. And W star transpose x test is basically this. Let me write it as test transpose W star. Okay. Because in whichever order you do that dot product, it will be the same. So it will be x test transpose, and W star is phi of x alpha. Okay. So you are going to project your test data point also in the higher dimension. Then you have your phi of x, and then you have this alpha. Okay. So again here you will be getting this form of what is it is similar to your kernel function. Okay. So the prediction you will be going to make is for each data point and my test data point, you are going to find the kernel function value, and you are going to multiply it with corresponding alpha. You are going to sum this up for all the n data points that you have. Okay. So alpha I will lie in the dimension of Rn. N denotes the number of data points. That's why the summation will go till the n. Okay. What this term represents is we are going to get the kernel function value for each data point with respect to the test data point, multiply it with the factor of alpha I. Okay. And sum this up for all the data points. That will be the final prediction for the X test. Is it clear for everyone?
Yes, sir.
Let's quickly move on to week 6. So week 6, mainly we have the ridge regression.
Sorry to interrupt. May I please? I have a question to ask.
Yes.
Are we also solving questions alongside, or are we just covering the concepts?
For week 9 to 12, I have questions. Okay,
Okay.
for that part, I'm going to solve. If week 1 to 8, if you have any question from your end, you can ask.
Okay. Okay. Thank you.
So for the ridge regression, what is the change that happens with respect to the ridge regression and a simple linear regression case? First of all, tell me how you find the optimal W. how you find the optimal W in the ridge regression case.
That part that uh, actually X transpose, yeah.
Hmm. Then,
Yeah, uh, then plus
hmm,
lambda I,
hmm,
whole
hmm,
inverse. Yeah, then yeah, xy.
yeah,
Yeah.
very good. Okay. Only thing is we are adding this lambda item extra from the normal equation method in the simple linear regression case. Okay. So that's how you can find the W star in the ridge regression. And the loss function for ridge regression that is given is your simpler SSC. Okay. SSC is simply your X transpose W minus Y, the norm square. Okay. Plus you are going to add the lambda times norm of W square. Okay. We generally divide it by 2 because while taking the gradient, this 2 and 2 will cancel out. That's just for the mathematical convenience. Okay. So this entire term of the SSC, sum squared error, plus this lambda times this norm W square, where we are going to use the L2 norm. Okay. L2 norm is it's W1 square plus W2 square and so on. Okay. So that's the loss for the ridge regression. And how this lambda here takes it into existence is if you increase the value of lambda, okay, you are basically penalizing large coefficients. So your goal is what? You want to minimize this entire loss function. That is the sum squared error part and also this second part also. But if you are going to take very high value of lambda, then you have to make your coefficients value to be very small. Okay, so that your entire loss function can be minimized. And that's why as the lambda value increases, the coefficients value, that is the value of each W1, W2 till WD, will going to approach to 0. Okay. And if you're going to make your lambda value to be small, then in that case, your coefficients will have a free space to move, so they can be larger value in that case. Okay. So let me ask one question here that if your model is overfitting, so do you guys know what does it mean by overfitting?
Yes, sir.
High variance, low bias, I guess.
Yes, high variance, low bias. Very good. Okay. And that is basically your model is very complex model. Okay. So if your model is overfitting, then should you increase the lambda or should you decrease the lambda value?
Decrease the lambda one.
For
Okay.
overfitting, we should decrease. Yeah, for decrease.
Should we? Should not we increase the lambda value? So
No,
as
if
you
we
increase,
increase
yeah, what will happen?
lambda,
Hmm.
yeah, the opposite means just what you said. Yeah, that is correct. Yes, sir. If we decrease lambda, then it will become
Com
overfitting. If we increase lambda, then it will become underfitting.
yeah. So as you increase the lambda value, so as I said, my model is overfitting. So I want to penalize large coefficients. I want to reduce the complexity of my model. So for that, I have to reduce my coefficients values. Okay. So as you penalize more, so you have to add more regularization. Okay. So for that, you have to set lambda value to be high so that my coefficient value will be lower. Okay. So the complexity of my model will reduce. Okay. So does the overfitting case. Okay. Now, if my model is underfitting, then I can reduce the value of lambda. Okay. So is the relationship bit is clear? What happens if you increase the value of lambda? Your model will become simpler. If you decrease the value of lambda, your model can become complex. Okay. So,
So
and
if
then,
model will become complex, then it is overfitting.
yes.
Okay.
So as, yeah. Any doubt here?
No, sir.
So as the lambda increases, the coefficient's value decreases or approach to 0. Okay. So this will also decrease the complexity. Okay. Just do the opposite case, everything will happen in the opposite way. Now what changes in the lasso regression case here?
Norm will become L1 norm.
Yeah, everything will remain same, that loss is SAC times square error plus lambda times. Now here it will be L1 norm. L1 norm means it's the summation of absolute values W1, W2 plus WD. Okay, summation of absolute values. Now the lambda again will work in the same way that it was working in the case of ridge regression, that as you increase the value of lambda, okay, it will penalize more your coefficients. But the only difference between ridge and lasso is what? Ridge only shrinks the coefficients, while lasso can make some of the coefficients value to be exactly 0. Okay, so the output or the solution that you got from the lasso regression will be a sparse solution. Sparse solution means it can have a coefficient value which will include some zeros in between. Okay, so if you have a question something like in which you have given different weight vectors and you have to identify which one is the solution for the lasso one, which one got from the solution of ridge regression, which one got from for the solution of simple linear regression, then the weight vector which contains more zeros will correspond to the lasso regression one, because the lasso is the one which gives the coefficients or which forces the sum of the coefficient value to be 0. Okay, and how you identify between the ridge one and the linear regression one?
Ridge has lesser values.
Lesser value. Okay, and the better way would be if you check for the norm. Okay, whichever has the least norm, that would be the corresponding to the ridge one. Okay, so yeah, norm of the ridge one would be less than the norm of the simpler linear regression one.
Sir, here norm only direct norm, lambda
L to norm.
norm or lambda
L to norm.
square.
Norm you can take any value, like whether you take the norm square or simpler norm, because in that case comparison, you will be getting the same answer.
Sir, if you are given such values and if none of them contain a zero, is it still possible to have a lasso regression in it?
Uh, if none of the option contains the 0, 1, then the one which will be like closer to 0, that should be selected as the lasso.
Okay,
But
sir.
I don't think so that they are going to give such a confusing options in that case.
Okay, sir. Thank you.
Any more doubt in the region lasso? Just remember how the lambda controls the overfitting and underfitting case. What happens if you increase the value of lambda? What happens if you decrease the value of lambda? The loss function. What type of solution does this give? Okay. So one thing that is remaining from week 6 is the cross validation. So what different type of cross validation methods are there in the MLT? Low CV, that is leave one out cross validation, and any other?
K fold is also there.
Yeah, K fold is also there. So can anybody explain what does low CV do?
Yeah, for every iteration, we leave only one point out for the S validation.
Yeah, very good. So as the name suggests, leave one out. So for my entire data set, I will left or I will leave one data point aside for the validation purpose, and the remaining data points, that is n minus 1. If I have n data points, I will keep one data point for the validation and remaining n minus 1 data point for the training purpose. Okay, so from the set of entire n data points, I will keep one for validation and minus 1 for the training. Okay, this process will continue until each data point is used for the validation purpose. Okay, that's what the loop CV method does. How many models are going to train in this case for one hyperparameter tuning part?
Yeah, for first time, yeah, we are going to train all, but we will do only n minus 1 by leaving one, isn't it?
Uh,
N models now.
N models. That's the correct one. If my question was not clear, let me repeat it again. What I am telling is these two are basically the method when you are going for the selecting the hyperparameter value. Hyperparameter are such as the lambda value here, because this is a hyperparameter. This is something that we do not learn from the data. It's something that we set from our side. Okay. And how it is said that we will be choosing some values of lambda, let's say 0.1, 1, and 10. And for each value of lambda, we will do this cross validation method. Whichever value of lambda returns the best score or the minimum error, that value of lambda is getting returned. Okay. So what I was telling that for if I am training using one value of lambda, let's say 0.1, and I am training using the loop CV method, then how many different models are going to train? And the correct answer for that was the n models, if you have n data points. In general, it's basically the number of data points that you have. Because what we are doing is we are setting one data point for the validation, the remaining n minus 1 for the training, and this process continue until each data point is used for the validation. So basically your for loop that you are going to run, okay, would be your basically until each data point is used for the validation. So that's why it will run n time. Okay. So for one value of lambda, there would be n models trained. Okay. And after that, you are going to take the average of the error that you are going to get from each of these n different model, and that will be the error for this value of lambda. Similarly, you are going to do this for the next value of lambdas also, and whichever is going to give the minimum average error, that will be the value of lambda that you are going to select. Is it clear?
Yes, sir.
Yes, sir.
Yeah. If something is not clear, you can tell at any time. Okay. Next is scaffold. How does scaffold works? You have your data set and you will divide your data set into some folds. Okay. Folds is it's like some parts, some division that you are going to do. So let's suppose if you have 1,000 data points and I'm doing a four-fold cross validation. That is, I will going to divide my 1,000 data points into 4 parts. So how many data points each of the part will contain?
250.
Yeah. So I will be getting 250 data points in each of my parts. Okay. Then similar to the loop CV method, what we are going to do is we are going to train on uh, k minus 1 fold, and the remaining fold is used for the validation. Okay. So k minus 1 fold is used for the training purpose. The remaining fold is used for the validation set. And this process, similar to the loop CV method, continues until each fold is used for the validation. So let's suppose I initially took these 3 folds, that is in total 750 data points for the training, the last fold for the validation. Then I'm going to use these 3 folds for the training, this for the validation. Then again, let's suppose I'm taking this, and this one for the training. Still, it is not completed because The second fold is not used for the validation yet. For in the next one, I can take these three for the training and my second for the validation. Okay. So main idea is same, that we are going to train the models until each fold is used once for the validation purpose. Okay. For again, for different values of lambda. And in the end, we are going to take the average of the error. Okay. And that will be the error corresponding to one value of lambda. And whichever lambda got the least average error, that value of lambda you will select. Okay. So k-fold is similar to loop-fibi method. If I set my number of folds to be equal to what?
N.
Very good. So if I am telling that I am doing n fold cross validation, that is I'm going to divide my data points into n different folds. That's basically same as one data point belongs to one fold. So in that case, my k fold will be a replica of leave one out cross validation. Okay, because k minus one fold, that's basically n minus one data points used for the training. Remaining fold, that is the remaining data point for the validation, and it process continue. Okay, so that was the main thing in the cross validation. Anybody has any doubt?
No, sir.
Hmm. So let's move on to week 7. So week 7 main algorithm was the KNN, K nearest neighbor, and the decision tree. Okay. So how you perform the KNN? How it is done? Anybody wants to explain first?
Uh, we are taking the points. We have KNN is first of all we are making a, group, isn't it? Then we are taking that point, one point, which group that point should belong, isn't that things?
Uh, okay, I think you are mixing the K means here. So okay, no problem.
Take the k nearest neighbors of the point and see what is the maximum level. Is it +1 or -1 between the
Yeah,
neighbors? And that will be the label of that X
mhm,
test.
correct. So you have some, suppose, red data points here. Then you have some green data points here. Okay, and you have some green data points here also, and some red data points here also. Okay, how does the KNN works is, for any given test data point, okay, I am going to find the distance of this test data point with respect to each and every data points that I have in my training set. So for my test data point, I'm going to calculate the distance with respect to each data point, and I will find the k nearest data point. This k is a hyperparameter. It can value any odd number. Generally, we take the odd number to avoid the case of tiebreaker. So 1, 3, 5, 7, like that. So let's suppose if I'm choosing the k value to be 5, that means I'm going to extract the 5 nearest data point for my test data point. So if this is my test data point, the closest 5 neighbor for this can be this one, this one, this one, this one, and maybe this one. Okay. In general, you are going to calculate this using some kind of matrix. It can be the Euclidean distance or Manhattan distance. Okay. So once you identify the k nearest neighbor, okay, what you are going to get is the label of these data points of the nearest neighbor, and whichever label got the majority. Just like here, my green label got the majority, as out of these 5, 3 has the green label. I will select the label for this test data point to be green. Okay, so that's how the KNN works. Any doubt in the KNN? Okay. Now a quick question. If I increase
Sir,
the, yeah, yes.
sir, I am telling that suppose in KNN test in this point, like this question, if
Mm-hmm.
given 2NN, if given we
Mm-hmm.
have to take 2 points, two
Mm-hmm.
nearest point,
Yep.
and that two nearest point we are getting one red and one green.
Mm-hmm.
So that time, which point should we follow?
Uh, the detail about this will be given in the question that what should be done in the case of tiebreaker. Otherwise, generally we go with the odd number of case to avoid the tiebreaker scenario. Okay. Any more
Okay, sir.
question? So now a question from my side. If I increase the value of k, so I have some values of k that's like 1, then 7, let's suppose, and then let's say 50 or 100 like this. Okay. So what can you conclude about the decision boundary that you are going to get in terms of the complexity of the decision boundary? Like the decision boundary shape or the model that you are going to get when you have a small number of k, will it be complex or will it be complex when you have a large number of k?
So when we have a large number of cases, then
Yeah,
it
large.
becomes more than, right?
Mm, okay. No, it's uh, in the opposite case that when you are having a small number of k, then you're going to get the complex decision boundary. So it's the opposite. Okay. So let me show one quick visualization for this. Uh, here. Okay. Now the reason behind thing you can understand from this neighbor part. If you are going to choose a very small value of k, okay, it's need not to be the one, like it can be 3 or 5 also. So then you are only considering very close neighbors. You are not asking many person to predict for the label. You are only asking the 1 or 2% to predict the label. Okay. Then in that case, as there are many different data points that are coming in from this blue regions data points. Okay. So the decision boundary you will be getting will be very complex, right? Because for each of these red data point, okay, it will have its own region of red here because we are only asking for one neighbor. Again, for this red data point, it will only have this region of red because it only asking for one neighbor. Okay, so very small spots of the red or the blue in between will be got created when you are only asking for a small set of data point. While will you move on to the very high value of k, as you are considering many data points to predict the label, and for this, let's say this red data point here, as it all its neighbors are surrounded by blue, the predicted label for this data point will be blue. Okay. But while in the case of when you have a value, small value of k, its predicted value was red. So that's why, as you can see, the decision boundary that you are getting is very complex here. If decision boundary scenario is very complex, then of course your model will be very complex. Okay. So as you increase the value of k, the simplicity increases in terms of complexity for your model. Model will become more and more simpler as you increase the as you increase the value of k. Is it clear?
Yes, sir.
Okay. Now, one small note that with k equal to 1, okay, we can achieve the misclassification error to be 0 on the training data. Okay, remember this term, on the training data only. Yeah. So if no more doubts, then I will move on to the decision tree part. Okay. So let's first understand the tree structure that we have. Okay. The upper node or the topmost node is called as the root node. Okay. And what you are going to do in the decision tree is you are going to ask some kind of question. That question will be answerable in the form of either yes or no. Based on how your data point answer the question, whether it is answer in the favor of yes or in the favor of no, you are going to split this node. Okay, so each node will be splitted. Again, from the splitted node, you are going to get some data point which have answered this question one as yes. Among these data point, again you can make the split and you can keep on continuing. Okay, so this is how the general design tree works. Okay, so these all Q2, Q4 and Q3 are called the internal nodes, and the nodes which does not have any further split are called the leaf node. Okay, so Q1 was the root node because it does not have any parent. Q2, Q3 and Q4 are the internal nodes because they have both parent and the child. L1, L2 and L3, L4, L5 are called the leaf node because they does not have any children. Okay, that's the general terminology for the trees. Okay, now comes the part how you decide this question. Okay, that how you will conclude that this is the question that you should ask, because in general you can ask for like any random question, right? So for that we introduce the measure of entropy, that is our measure for impurity. Okay, again it has some notations. Okay, that is NP, that is the number of positive data points, and N, that is the number of negative data points. Okay, so in any node you will have two classes, positive or negative. Okay, so NP is the number of positive and N is the number of negative. And if we define what is called as the proportion, that is the fraction of positive data points. You can define it in terms of negative data point also. The answer will be the same in that case also. Okay, so whether you define your proportion as the fraction of positive data points or the fraction of negative data points, the overall answer does not change. But the default convention that we are following is my proportion is with respect to positive data points. Okay, so entropy for a node is given by this formula, negative p log 2 p minus 1 minus p log to 1 minus p. P here is this proportion value. We choose the base for the log to be 2. Okay, and as you can see, this formula is symmetric. Okay, so whether you choose the proportion to be the positive data point or you choose the proportion to be the negative data point, it does not change. Final answer will be the same. This is the geometric view for this impurity. Okay, if my proportion is 0, what will be the value of entropy?
Point 0.5
No, for if my proportion is 0,
Zero, zero.
Zero.
0, right?
yeah, yeah, yeah.
What does it mean by proportion to be 0? That means this NP by N is 0. So NP by N is 0 means there is no positive data point in my node. Okay, so if there is no positive, that means all the data points are negative. So my node contains all the data points which are negative. So my node is already very pure. Okay, similar case when happen if you choose the proportion to be 1. 1 means all my data points are positive class, does not have negative. Okay, so again it is a pure node. Okay, so if your node is pure, that is all the data points belongs to one class, then you are not going to make any split, right? In that case. Okay, so when you consider your node to be the most impure, then when you have an impurity of 0.5. 0.5 means half of your data points belongs to positive, half of your data points belongs to negative. And in that case, as you can see the graph, the entropy value will head to 1. That is the maximum entropy value you can get. Okay, entropy value here lies between 0 to 1. Okay, so at the case of 0.5, because in that case you cannot predict what should be the uh, class for your any test data point, because you have 50% chance for it to be positive, 50% chance for it to be negative. So that's the most impurest case you can get. Okay, so till now, anyone has any doubt?
No, sir.
So then comes the question part that I said, how you define whether your question is good or not. That is defined using the information gain. So again, some terminology here. Gamma, that denotes the proportion of the data points going into the left child. So you have this parent node that you want to split by using some question. Question will be in generally in the form of that whether my feature, some feature value is less than some quantity or not. So let's suppose if you have like the runs of cricket made by some player, then you can ask the question whether my uh, batsman has run uh, the number of runs he has made is less than some quantity or not. So like these type of question, okay. Or for the categorical feature, you can ask the question whether uh, this feature has this particular category or not. Okay, so these kind of question you are going to take, and for each of these question you are going to calculate the information gain. Okay, so each question will result in the split of this node, in which some data points will go into the left child, some data points will go into the right child. Gamma denotes the proportion of the data points going into the left node. NL is the number of data points in the left node, and R is the number of data points in the right node. Okay. EP, EL, and ER, these are the entropy for the parent node, left node, and the right node. So information gain is given by the entropy of the parent node minus the summation of weighted entropy of left and right. So gamma times the entropy of left node plus 1 minus gamma times the entropy of right node. So we are not just subtracting the entropy of left and right child from the parent child. We are weighting them by the fraction of data point they belong. Okay, so as the gamma belongs to the fraction of data point in the left child, we are weighting the entropy of left child with the gamma. And for the right one, we are weighting it by 1 minus gamma because that is a fraction of data points going into the right node. Okay, so this is how you ask the question. If I told about how you make for the prediction for any test data point, you are going to follow this graph. That is, for each for my test data point, I am going to ask the question whether what is this question, and based on that, I am going to iterate through this graph. And let's suppose by iterating, I am going to reach some kind of leaf node. Okay, in that leaf node, whichever class has the majority, that class will be the predicted class. Okay, yeah. So that's about the decision tree. Any doubt here? Okay. Now some of the key properties that it can achieve zero misclassification error on the training data. And one more thing, that it can be overfit easily if you increase if you allow your tree to be grow till maximum height. Or by maximum height, by that I mean is until you get a pure node. That is until you get a scenario where all the data points in my current node belongs to one class. So if you allow your tree to grow in this type of scenario, then it can easily overfit. Overfit again means it will be having high variance, will be a very complex model. Okay. So let's move to week 8 if that is completed. So yeah. So the main topic was in week 8 is first started with the difference between the discriminative and the generative models. Then we move on to the naive Bayes and the LDA. So if I just give a brief overview of what is mean by discriminative and what is mean by generative model, then discriminative, as the name suggests, it discriminate between the classes. Okay. The goal in the discriminative model is to find a decision boundary that will separate your classes. Okay. So just like the example here given, for your set of data point, you are going to find some kind of decision boundary. It need not to be the linear one, but a simpler example here would be the linear, as that what we are studying in our course. Okay, but it will try to find some kind of decision boundary which will separate my data point class. While in the case of generative model, we try to see that given the data point, how my classes will look like. Okay, or basically how my data points are getting generated for a given class. Okay, so that's what we do in the case of generative model. We try to see the generative process for my data point. For discriminative, we do the discrimination between classes. Generative, we see the generative process for my data point for each of the my class. Okay. So any doubt here? Okay. Now, one very kind of like a famous question that they ask quite often was about this parameter calculation part. Uh, that is one when we do not assume the class conditional independence and when we assume the class conditional independence. So class conditional independence means given the class, my features are independent. Okay. So okay, I think I have to move to pad. So for week 8, so when class conditional independence is not assumed. Okay. So that is the probability of given the class my features like x1, x2 till xt. Okay. Oh, let me take the f1, f2. That would be much better. F1, f2 till ft. Okay. This would be probability of f1 given y times probability of f2 given y multiplied with probability of fd given y. Okay. This is what class conditional independence means. Given the class, my features values are independent. So if you do not assume this case and then try to predict the number of parameters for your model, then first thing that you need is the probability of class. Okay. So assuming you have binary classification problem, okay, then you need the probability of class prediction that what is the probability of y equal to 1 or what is the probability of y equal to 0. So in that case, how many parameters will come? 3 parameters. How many free parameters will there in the case of class prediction probability? So as we are taking with the binary classification problem, you will be having one probability for y equal to 1 and one for y equal to 0. Okay. So technically there will be 2 parameters, but because of the probability rule that the probability will sum up to 1, in general the free parameters that you are going to get would be 1 from this class case. Okay. Then you are going to calculate the probability for each of my data point having some feature value f1, f2 till ft given the class. Okay. You have to calculate this probability then. Okay. So let's take the simpler case where my each feature are binary. Okay. So for is f1 till fd, they can take either value 0 or they can take either value 1. Okay. And I have d such feature. Okay. So can you tell how many different combinations you can make from here?
2 to the power d.
2 to the power d. Because we have d features and each of my feature can take values between 0 and 1. So each will have two choice for feature 1 and feature 2. Like that it will have till d. So it's become 2 power d. Okay. So you can make 2 power d different combination. Okay. For one class. Okay. Now similar case will happen that you will be making 2 power d combination for the class 0 also. Okay. So for the probability of x given y, there will be 2 power d parameters. But again, for the case that this will sum up to 1, okay, you will subtract the minus 1. But this is for, let's suppose class equal to 1. Same thing will happen for class equal to 0, 2 power d minus 1. Okay, y equal to 0. Okay, so if you go with the total parameter calculation, it will become 2 into 2 power d minus 1 and plus 1. This plus 1 is for this class probability. Okay, this 2 is because we have two classes here, and each will have 2 power d minus 1 parameters. Okay, so is it clear how this parameter calculation is working? If you are clear about this binary classification case, you can extend this idea to multi-classification also. Okay, now let's go with the second case. Then class conditional independence is assumed. Okay, so in that case, what will happen? That this scenario will become true. Okay, so we have to find only these probability of my feature 1 given y, probability of my feature 2 given y, and so on. So you can think each of these probability as some kind of coin toss example, that you have a coin, okay, which gives that given the class to be, let's suppose, 1, my feature 1 can either take value 0 or either it can take value 1. Okay, so it's some kind of coin which one side it will give that probability of f1 to be 0 given class to be 1, and on the other side it gives the probability of feature 1 to be 1 given the class to be 1. Okay, so how many parameters for one such type of coin will be there? It will be only
N
one
coin.
because for one coin I'm asking, it will be just one, right? For
Yes, sir.
one such coin, it will be one, and because we have d features, so in total d coins you need, right? Okay, so we have to find this probability of x given y, which using the class conditional independence, I can break it down as probability of f1 given y and probability of f2 given y, and so on. And because each of these only have one free parameters and we have d features, so it will become d parameters we need for one class. Okay, so same thing will happen if you are going to consider the class of y equal to 0. You'll again need d parameters. Okay, so the total params in that case will become 2 into d and plus 1 again for the probability of y equal to 1 or y equal to 0. So this is the class probability. This is for the given the class, what is my feature values are going to take. Okay, so is this clear? The parameter calculation for the class conditional independence. Okay.
Yes, sir.
Mm. Uh, if you have any question from week 8, you can ask, but with me, I only have question from week 9 to 12. Okay. After finishing week 8, we will go with both theory and question for week 9 to 12. Okay.
Yes, sir.
Now comes how you implement the knife base. What you are going to do is you will be given some kind of table. Okay, where let's suppose these are like my feature 1, feature 2 values, and similarly you can have more feature. And one section will be for label. Okay, so label have two classes. Let's suppose yes or no, yes, no kind of. First thing that you are going to estimate is the probability of class. So let's suppose probability of y to be yes. So that you can decide based on the fraction of yes among all the data points. So if you have 5 data points, let's suppose here. Okay, out of 5, 3 are yes. So probability of y equal to yes would be just 3 by 5. Okay, so probability of no would be what?
2 by 5.
2 by 5. Okay, so you estimated the probability of class. Okay, it's simply the uh, fraction of your class. Well, now we have to calculate this value. Okay, that feature one take this value given the class. So let's suppose, let me add the feature sum here. A, B, A, B, A. Okay, so my feature one takes two value, either A or B. Okay, so if I want to find the probability of feature one to be A given the class to be yes, okay, how you are going to calculate it? You will be seeing out of all my yes class data point, that is these three, how many of them are taking the value yes. So this one is taking yes, this one is taking A. Okay, so out of all the three yes data point, only two of them are taking the feature one value to be A. So what will be the probability then?
2 by 3.
2 by 3. Similarly, you can calculate the other probabilities in this manner. So if they ask for the estimation like this, I hope you can answer the question now. The other type of question that can be made from here is, what is the probability that given the data point, my class would be yes. Okay, I'm taking the yes as an example, but it can be like 1, 0 or anything. Okay, so here you have to apply the Bayes theorem. So what would be the Bayes theorem equivalent form for this probability?
Bayes theorem, there's probability of yes, and then probability yeah.
So it would be probability x given y is equals to yes
Hmm.
into probability of y is equals to yes by probability of x.
Yeah, and what will be the probability of x here? It's basically the total probability, that is x y equal to yes times probability of y equal to yes plus probability of x given y equal to no times probability of y equal to no. Okay, that's basically at x. What is the probability that x belongs to yes class, and what is the probability of x belongs to no class? Summation of these two. Okay, so
Sir, one question.
yes.
Sir, actually, I get sometimes confused that whether I should use this Bayes theorem or should I use that joined by this total mass. There is one more formula, isn't it, for this type of question? So when should I use that one, and when should I use this one, Bayes one?
Okay, I think you are asking for when you do not consider this normalization part.
Yeah, no. I'm telling that there was one question, isn't it? This is a conditional, and into the conditional is equal to joined by marginal. So,
No,
so
no, no.
this,
Generally, that I don't think so. We use that formula here. Like, okay, what we know here
yeah,
is this probability that given the class, what are my feature values they take? Because just like we found this value, okay. Similarly, you can find for the other features value, and in that case, you will be able to find this probability of x given y equal to some class value, and you know this value also, and the total probability also we can calculate. Okay, but the one that you are saying, that conditional equal to joint times marginal, we do not know the joint probability here, right? Probability of x comma y, right?
yes, sir.
Okay, so that's why go with this one. Okay. And this probability is used when they are saying that given my data points, what is the probability that it will have the class yes? Okay. But sometimes question just asks for the label. What will be the predicted label? Okay. They do not ask of this probability. They just want the label. So in that case, what you can do is you can skip this normalization part, and you can only calculate the numerator value and compare it with the other class numerator value also, that is the y equal to no class. Whichever got the highest numerator value, that will be the predicted class. Because the normalizing constant in both the case for y equal to yes and y equal to no will be the same. So that's why we are only comparing the numerator part for predicting the label only. Again, I'm emphasizing it. If you just want the label, only in that case scenario we compare with the compare with the numerator class. Okay. But if you want the entire probability, that the probability of y equal to yes given the data point, then you have to include this normalization part also. Okay. I hope it is clear.
Yes, sir.
Yeah. So due to the time constraint, I'm directly moving to the week 9 part now. Okay. So let's quickly revise the concept, and then I have some questions from week 9 that we are going to solve. These are some from PYQs. So the two main algorithm that we studied in week 9 was the perceptron and the logistic regression. Okay. So can anybody tell me how the perceptron algorithm works? How do you do the perceptron algorithm? Given the set of data points x1, x2 till xn, and the corresponding label y1, y2 till yn. Yes, that's the geometric view.
Sir,
So,
uh,
Hmm?
you have a label of y which is either +1 or -1. Um,
Yes,
and then you basically do the learning update, which I call it, where if the prediction is correct, you don't do anything, and if the
yes,
prediction is wrong, you update the weights.
very good. Okay, so first step would be the initialization of your weight vector. Again, if nothing is given, you will initialize it with the 0 vector, or else initialize it with whatever the weight vector they have given. So I'm taking a simpler case of 2-dimensional. Okay, so my weight vector we will initialize. Then the next step is we will find this quantity W transpose X. Okay, if and we will calculate the sign of this, the sign of W transpose X. Okay, that is if this quantity is greater than equal to 0. Okay, then the label would be 1, or else the label would be 0. Okay, or here if as we are removing the 0 case with the -1. Okay, the main purpose for removing it with the -1 was to prove the convergence of the perceptron algorithm. Otherwise, you can work it around with the 0 also. Okay, but let's stick to the notation that we have the label in the form of -1 and 1. What we are going to calculate is the W transpose X value. If this is greater than equal to 0, or basically you can just infer the sign of that, then the predicted label would be 1. Okay, greater than equal to 0. Prediction would be 1. Okay, else the prediction would be -1. Okay, if it is a correct prediction, do not do anything. If it is wrong prediction, then we will update our weight vector. And what is the update rule for perceptron?
Sir, W1 is equal to W0 plus WIXI.
Uh, XIY,
XIYI.
XIYA, right?
Sorry, yes.
No problem. Okay, so you get the W1. Now you are going to use W1 for the further cycle. Okay, so in remember one thing in this case, that cycle through the data point in the given order. So if my data points are given in this order, I'm going to cycle through them I'm going to cycle through them in the given order only. So that is x1 first, and x2, and like that. If x2 is given first and then x1, then cycle in that order, because cycle is important. The order in which you are going to cycle through your data points, it can change your final weight vector also. Okay, one thing that is important. Another thing is, after updating at any point of time, you are going to start the cycle from the next data point that is supposed to come. That is, suppose you are updating your weight vector at the third data point. Okay, then you will start your cycle from your fourth data point. That is the place where you are supposed to start or continue. Do not do like the restarting thing. Okay, for two things. Yeah, that's all is there in the perceptron. One quick question: does perceptron gives us? Okay, sure. So what I was telling, that cycle is very important in the perceptron. The order in which you are going to cycle through your data points. Okay, at the given order is this x1, then x2, then xn. Okay, but in the question they can ask also, like, first let's say you take the data point x2, then you take the data point x1, then x3, like that also. Okay, so in whichever order they have mentioned, cycle through your data point in that order only. Okay, because based on how you cycle through your data point to calculate this value, it can give you a different weight vector also. Okay, so cycle in the given order, one thing. Second thing was that let's suppose you got the wrong prediction as okay, let's remove this one. You are cycling through in this order, x1, x2, x3, and so on, and then you got the wrong prediction as some x3 data point. Okay, then you are going to update the weight vector as follows. Then you have to restart your cycle from the next data point only, that is start from the x4. Do not do like I'm again going to start from x1 and go till x3 like this. Okay, resume your cycle from the point where you left. Okay, so I did with x3, so I should start with x4. Well, so one quick question: does perceptron gives you optimal weight vector?
Yes.
Answer is no. Okay, perceptron does not guarantee for an optimal solution. Okay, one thing. Optimal solution
It
can,
stands.
sorry,
Oh, so it goes to near, isn't it? But it
uh,
doesn't guarantee.
it does not necessary to be near also, like it can be very far also. So, but only thing you can say that it does not necessarily gives you the optimal solution. By optimal solution, we mean here that if you have these data points where some of them are red here, okay, some of them are green here, okay. So perceptron can give you any linear classifier. It should supposed to be from origin because we are not concluding the case of bias in our course. Okay. So perceptron can give you any valid linear classifier. It can be this one also, can be something like this, which will basically separate the two classes. But it does not necessarily to be the optimal one. Optimal one we consider in which it generalizes better for the unseen data point. And that usually happens when you have a large margin scenario. Okay, that is the case in which your linear separator line, okay, the margin between the closest data point to this line will be maximum. Okay, so in that case scenario, that is considered as the optimal solution, and that perceptron does not guarantee. Okay.
Oh, sir, actually, so whenever we will see the guarantee, what we can say directly that things may not work, isn't it?
uh, it does not necessarily always, because logistic regression and the SVM both gives you the optimal solution. Okay, but only the perceptron does not give. Okay, Yeah.
Yeah, okay,
So
sir. So logistic and regression.
yes, yeah,
So if we use that in that way, is there suppose someone is using this guarantee word in that logistic and regression, then it will become true, isn't it?
yeah.
Okay, sir.
Okay. Unless some other conditions are not given, which are making it false. But for the logistic, it will converge, and it will give you the optimal solution. For the perceptron, it does not guarantee that it will give you the optimal solution. Now, second thing, perceptron only works on the linear separable data. Only when your dataset is linearly separable, only then the perceptron algorithm will converge. Otherwise, it will not converge. Okay. Convergence simply means is there's no update in the weight vector in one full cycle of your data points. Then it shows that it is converged. Yeah. So these two are the main fact. If we talk about the logistic, then the need of moving from the perceptron to logistic was perceptron was kind of a hard solution. The what does it mean by hard solution is that it gives the scenario of between 0 and 1. So either 0 or either 1. Okay. So either you are going to get 0 or either you are going to get 1. You're not in between somewhere. Okay. So introduce the notion of probability. We move to the logistic regression. Okay. The only thing that changed from perceptron to logistic regression is we make use of the sigmoid function. Okay. So instead of using the W transpose X, we use the sigmoid of W transpose X. Okay. And set some threshold value theta. And if my this value is greater than my threshold value, then I will predict the label is 1. Okay. Else I will predict the label is 0. In the logistic, we again come back to the case of label to be 1 and 0. But again, labels are something that we can decide. So you can keep it as 1 or -1 also. No problem. So how you define your sigmoid function? 1 upon 1 plus e power negative W transpose X. Okay. So this is the sigmoid value function. And it always lies between 0 and 1. Okay. This is the line y equal to 1. Okay. This is the line 0. So sigmoid function value always lie between 0 and 1. So it will give you a probability.
So both are exclusive.
No, 1 is not included and 0 is also not included. It's an asymptote to both of them. It does not touch it. It approaches, but it does not touch it. Okay. Yeah. And it can work on non-linearly separable data set also. Okay. That's one more thing. Okay. So should we move ahead to the some question?
Yeah, sure, sir.
Finally, we have some question. So consider a training data set of, okay, let me mark one thing that this is a paper of May 2024. Okay. So consider a training data set of 100 data points for a binary classification problem with the following features that they are in R2 and the labels are -1 and 1. For each data point x1, x2 in the training data set, it satisfies two conditions. X1 times x2 is greater than 0 and x1 times y is greater than 0. Okay. So you have given only these conditions. Based on that, you have to basically tell that whether my data set is linearly separable with the positive margin or whether it is not. And once if you are able to prove that my data set is linearly separable with some positive margin, then of course perceptron algorithm will terminate or converge on that. But if you think the data set is not linearly separable, then of course the perceptron algorithm will not converge. So what do you think? Is the data set linearly separable here or not? With respect to given these two conditions.
first one may become maybe correct, isn't it? First one,
Why
the
do you
data
think
set
so?
is, yeah, because this x x and x2 and x1 and x1 and xy are both both are different side. So for that, I am telling that this is separable.
Okay, so very good. So if we look at the first condition that x1 and x2 both are greater than 0. Now because it is a 2D data set, okay, the values of x1 and x2 in terms of sign, if I talk about, okay, any data point either can lie in first quadrant, second quadrant, third quadrant, or fourth quadrant. In the first quadrant, what are the signs that the data point can have? Sign only. It will be positive, positive, right? Because both the x value and y value here would be positive. What about second?
It's
Negative,
positive, negative.
positive,
Minus plus.
What about third?
negative,
Both negative.
negative,
Fourth?
positive,
Positive, negative.
negative.
Hmm.
Positive, negative.
Now, given the condition, then x1 into x2 is greater than 0. Okay. X1, x2 here does not represent the data point. They represent the feature values here. Okay. So these are the feature values here. Okay. So if they both are greater than 0, okay, then what do you think in which quadrant they should lie?
So either first
First or third.
First or third? Because if you say the product between the feature values in second and fourth quadrant are negative. So either my data point can lie in first quadrant or either they can lie in third quadrant. And because of this condition that x1 is greater than 0, okay, sorry, this strict condition of greater than 0, okay, they will not lie like around this point, like at the origin. They will lie at some distance from the origin. Okay, so that was the one thing. Now, what does the second condition helps us? First condition helps us identify that either my data point will lie in the third quadrant or either they will lie in the first quadrant, and they will be not like at the origin because it is not equal to 0. Okay. What does second condition helps us identify?
Plus one label to all data points in first quadrant.
Very good. Because my labels are -1 or 1, okay, if for any data point which lying in the first quadrant, its label has to be 1 only. Only then it will satisfy this condition that x1 times y is greater than 0, right? So all my positive data points will lie in the first quadrant, while all my negative data point will lie in the third quadrant. Because in the third quadrant, my first feature value is -1. If only my label is also -1, then only this condition will satisfy. So all the negative data points will lie in the third quadrant. So using these two conditions, we are able to identify the position of the data points also. And also one thing that because these are values not equal to 0, so that means there would be some margin. Okay, some positive margin will be there between these two classes of data points. Okay, so that's why the first option will become true. Okay. Now, once we know that our data set is linearly separable with some positive margin, the question about that whether the perceptron algorithm will terminate or not, okay, I hope you can answer that it will always terminate. Okay, perceptron algorithm will terminate after a finite number of iteration when trained on this data set. Okay, is this question clear to everyone?
Yes, sir.
So could you just repeat the positive margin part?
A positive margin. So because in both the condition it was greater than 0, so that means none of my data point will lie on the either the axis, because let's suppose if you take any data point which have like -2 comma 0, okay, for that this condition fails, that greater than 0, because it will be equal to 0 in that case. Okay, So what these two condition of strict greater than 0 tells us that all of these data point will lie uh, somewhere like this, and from the first quadrant side they will lie somewhere like this. Okay, so there will be some positive margin between them because of this strict inequality case here.
Yes, sir. And if it was greater than equal to 0, then we
Yeah,
could say
then
that the
you cannot
margin could be 0.
yeah, confirm about the margin case.
Okay,
Margin
sir.
can be 0 in that case. Okay, because then your data point can lie on this origin also.
Yes, sir.
Any more doubt from this part? Okay. Second question on the logistic regression, that we are training a logistic regression on the binary classification problem with the features in R2 and the labels for 1 and 0. The probability of the test data point 1, 1 belongs to the class 1 is given by or equal to 1 upon 1 plus e square. And which of the following could be the weight vector for this logistic regression classifier? So they have given this value 1 upon 1 plus e power 2. Are you able to identify some similarity between this value and the sigmoid function?
minus w power tx is equal to 2.
So in the logistic regression, we do the prediction as follows: that e power w transpose x is sigmoid of w transpose x is 1 upon 1 plus e power negative w transpose x. And they are telling that the probability that the test point belongs to class 1 is equal to this value. Okay. This is generally the probability of class equal to 1. For the class equal to 0, the probability would be 1 minus of this value. Okay. So this value is equal to 1 upon 1 plus e the square. Okay. So, and you have also given a test data point that is 1 comma 1. So from here you can identify that negative w transpose x should be equal to 2. W transpose x should be equal to negative 2. You have given your x. Okay. So you can take w1, w to be w1, w2, and x to be 1, 1. This should be negative 2. Okay. We'll get w1 plus w2 to be negative 2. Okay. So among the option, which are the weight vectors which results in this?
So first and second.
First and second. Okay. So anybody has any doubt in this question?
Sir, I didn't get it exactly. Like, can you just explain the options?
Yeah. So see, what they have given is that the probability for my test data point 1 comma 1 belonging to class 1 is equal to this value 1 upon 1 plus e square. Okay. And we know that the probability of a data point belonging to class 1 in the logistic regression case is given by the sigmoid function value of the w transpose x, that is 1 upon 1 plus e power negative w transpose x.
Yes.
And that probability is given as 1 upon 1 plus e power 2 here.
So equating that, we'll get wt power x equal to minus 2. That
Minus
is
2.
2.
And on simplifying, we get w1 plus w2 is equal to negative 2. X is given as 1 comma 1.
Achha, okay. We have to just input those values and we'll get the answer.
Yeah. And from the option, only the weight vector which satisfy the condition that w1 plus w2 is negative 2, those will be the correct answer. Okay. Any more doubt in this question? Okay. Now,
Sir,
uh,
I have
I
a question.
yes,
Um, I'm a little confused in logistic regression. So there is some threshold value also,
yeah,
right, that we compare
mm-hmm.
when it comes to labeling one or zero in logistic
Yeah,
regression.
mm.
So how does that also align over here? Because you said that there is some value that it takes when the label is one. So,
Yeah,
like, can you just explain that part?
okay, sure. So In general, see, based on different problem scenario, we can choose different threshold value that I will choose, or I will need at least this much percent of probability to select my data point to be class 1. So some use case scenario, let be like you are on airport security check, then you do not want any harmful product to pass through the security check. So in that case, you can set your threshold value to be some less quantity, because you are okay if some data point can be misclassified, but you do not want any harmful product to go to pass the security check without abruption. So in that case, you will set the threshold value to be some less quantity. Okay. And in some other case where you are okay if some of the zero class data point are, oh sorry, some of the one class data point are predicted as zero class, then in that case you can set the threshold value to be high value. Okay. So depending upon your use case and the problem statement, you can vary your threshold value, because this is the probability that you want this much percentage of sureness to predict it as class 1. Okay. Or else we will predict it as class 0. So that's how you make use of the threshold. If nothing is given as the threshold value, we generally take it as a threshold value of 0.5. Okay. And the question what they were asking is that the probability of my data point belongs to class 1 is this. Okay. That's basically this quantity of the sigmoid of W transpose X. Okay. The sigmoid of the W transpose X is what we call it as the probability of class 1. Okay. Here we do not make use of threshold because the question was not asking to make the final prediction. Okay. Instead, it was just asking for the probability of class 1. That is just the direct sigmoid function value. Okay. And if they ask for the class 0, then it would be 1 minus the sigmoid function value of W transpose X. Is it clear?
So, sir, if it is so if the label has to be zero, then the value would be 1 minus sigmoid of W transpose of X.
Yeah, correct.
Got it.
That would
Okay.
be the probability for it to be class 0.
Okay. Got it.
So there was one more question which was technically from week 10 point of view. So like it includes the SVM, but the main question again was asked from the perceptron point of view. Consider a linearly separable dataset with positive margin. The symbol alpha star I in the context of SVM has its fusion meaning. Okay. And whether the following statement is true or false, that's what we have to find out. The weight vector output by the perceptron algorithm on this dataset, that is the dataset which is linearly separable with the positive margin, can be expressed as a linear combination of my data points where the coefficients of the linear combinations are integers. So will this statement be true or false?
True.
Okay. So can you prove it? Okay. So anybody else? How it will be true? Okay. So let's go with the perceptron update rule. First of all, one thing we know that because my data set is linearly separable with a positive margin, so my perceptron algorithm will converge. Okay, so no doubt on that part. Now comes the how does it look? The weight vector. So we'll initialize our weight vector with 0, 0. Okay. Then if it has made any mistake, we will update it using the perceptron update rule, that is 0, 0. Oh, sorry, W1 is W naught plus for the data point which is making mistake times its true label. Okay. Now my W naught is 0, 0 vector. Okay. And then I have my, let's suppose this 1 and x2 here. And the label can be 1 or minus 1. Okay. Let's suppose the label was 1. So what will be my new W1, it will be now x1, x2 times 1. Okay. Now we will again cycle through the data points, and let's suppose again it has made some mistake. So again we are going to update it. Okay. Now my W1 is this x1, x2 times 1. And then I will have some different data point. Let me call it as x3, x4, and it will have some label. Okay. So this will be my W2. Now if you see, it is a linear combination of two data points on which it has made mistake, and in which the coefficients are either 1 or -1 depending upon the label for of that what will be the true label for the data point. So either it will be 1 or -1 specifically. Okay. If you extend this idea, okay, my weight vector that I will get after the perfect one, it will have the linear combination of all the data point on which it has made mistakes, okay, throughout the cycle, with the coefficients to be integers, and in more specific, they will be the true label for those data points. Is it clear how it will be true? Okay. Yeah. So that's all was there in the week 9. Okay. So we have then week 10. So week 10, the main algorithm that we studied was the SVM, support vector machine. Okay. In which I think, yeah, I know that this week would be quite mathematical, but we won't be asking you to solve any kind of mathematical optimization problem from this week. What you should main remember from this week was the results that we got specifically, and how does the primal and the dual problem looks like. Okay. So the primal problem for the SVM was min over W. Okay. The optimization variable in the case of primal variable was W. Max over alpha. Alpha is the constant that it should be greater than or equal to 0. Norm W square by 2 plus alpha I times 1 minus W transpose xi yi. Okay. So this was the primal problem for my support vector machine. Okay. And one more thing here, that this would be the summation from I equal to 1 to n for all the data points. Okay. In the dual, it's just a swap of min and max. It's the max over alpha greater than or equal to 0, min over W, norm W square by 2 plus summation from I equal to 1 to n alpha I 1 minus W transpose xi yi. Okay. So remember the primal form, remember the dual form. In the primal, the goal was to find W. That is, the primal variable was W. The dual variable is alpha. Okay. And after solving the dual problem, we will be getting the solution of W star as what it will be. What will be the solution of dual problem for the W star?
Alpha into X into Y.
Yeah. So
Summation of alpha into X into Y.
alpha I, xi, and yi. This was in terms of data point and label. If you want a matrix representation, it would be x, y, alpha, where x is again your data matrix, x until xn. Now y here would be a matrix in which it will be diagonal matrix specifically, where your labels are arranged diagonal. Other values would be 0. Alpha, it's a vector of alpha 1, alpha 2, well, alpha n. Okay. So these are the main thing. Alpha star, it will be given in the question most of the time. If they are asking something related to the W star, okay, they can ask question like they will give you alpha star And from that alpha star, you can find the W star value using this. Okay. Now comes the condition for the support vectors. Okay. So what are support vectors?
The
Which
points which lie on the hyperplane.
yes, okay. So that's the geometrically. Mathematically, how you will conclude, or what type of
The
condition that, yeah,
alpha is equal to 0.
alpha equal to 0 or alpha greater than 0?
Alpha greater than equal to 0 or less than equal to C
Uh,
maybe.
See, alpha has this constant that it will be greater than 0 in the dual problem. So it will not be less than 0. Okay. There will be two scenarios. One will be alpha greater than 0. Other will be alpha equal to 0 for each data point. Okay. So support vectors are those for which alpha star I value would be greater than 0. For all those data points for which my ith alpha star value is greater than 0, those are the support vectors. And those are the most important vectors because they support the linear decision boundary. They helps us make the final decision boundary. Okay. That happens in the case of support vector machine algorithm. That is, uh, you will have one here and you will have these, and on one side it will be red, other side it will be green. Okay, you will be having this W. Okay, so this line would be W transpose X equal to 0. This dotted line would be W transpose X equal to 1. This would be W transpose X equal to minus 1. These are called the supporting hyperplanes. Okay, and there would be support vectors which will lie on these supporting hyperplanes. Okay, and for the alpha star value to be greater than 0, only then they are called the support vectors. Okay. Now, can it happen that any vector which is lying on the supporting hyperplane is not a support vector? Or all the data points that lying on,
Yes,
okay, this
not
will
all
happen.
data points.
So
Not
not
all
all
data
data points.
points.
Very good. So this can happen for when the for those data points the alpha star value is 0. Okay, this comes from the complementary slackness condition among the KKT. Okay, so the KKT condition that we studied in MLF, the current Krushtaka. One condition was the complementary slackness condition. So the easiest way you can remember this condition would be, it would be the alpha times the constraint that we had on the data point. What was our constraint? Constraint was that all the data points lying on the different side of margin. So all the green data points lying on this side, all the red data points lying on this side. And together we can make the constraint as W transpose Xi times Yi to be greater than equal to 0. Right? And because in the primal and dual form, we take the constant to be like in the less than equal to form, or say not the less greater than equal to 1. Okay. So in the primal and dual formulation, we generally take the constant in the form of less than equal to 0. So that's why the final constant that you get would be 1 minus W transpose Xi Yi less than equal to 0. Okay. So the complementary condition is my dual variable times the primal constraint. So dual variable was alpha I, primal constraint was 1 minus W transpose Xi Yi. Okay, and we set this value to be 0. This is my complementary slackness condition. Dual variable alpha I times the primal constraint. 1 minus W transpose Xi Yi to be 0. Okay. So if W transpose Xi Yi is 1, that is my data points are lying on the supporting hyperplane. Okay. Then inside value would be 0. Okay. But alpha I, there is no constraint on the alpha I that whether it has to be 0 or it does not have to be 0. Okay. And that's why not all the data points which lie on the supporting hyperplanes will be support vectors. Okay. But if you said that my alpha I value is greater than 0, then it will force this inside condition of 1 minus W transpose Xi Yi to be 0, because only then the final condition of complementary slackness will be satisfied. So that's why we say that all my support vectors lie on the supporting hyperplane, but not all the vectors which lie on the supporting hyperplanes are the support vectors. Okay. So even if you forget in the exam, you can remember the complementary slackness condition and the condition for the support vectors and infer from that. Okay. So now comes the third condition, that what happens to the data points which lie beyond the margin or beyond this supporting hyperplane. What type of condition they will satisfy? They will satisfy the condition that W transpose Xi Yi value is greater than 1. Okay, because only then they are lying beyond this margin case. So if the inside value is not 0, it will force my alpha I value to become 0. Okay. So all the data points which does not lie on the supporting hyperplanes are not the support vectors. Okay. So is it clear for everyone? Then,
Yes, sir.
then let's solve this question. Consider the case of hard margin SCM. Okay, so I did not told about the hard margin case. So hard margin is basically when your dataset is linearly separable. Okay, that's the hard margin. So consider the case of hard margin SCM, that is your dataset is linearly separable. Okay, it is trained on a linearly separable dataset with positive margin. Two test data points are given below, the x1 and x2, along with the decision boundary and the supporting hyperplanes. And which of the following will be true? Basically, you have to predict the label for the both of the data points. So what will be the label for x1?
1.
1, right? Because it is lying in the direction of my weight vector. So that's why the label would be 1. X2?
-1.
Minus 1.
Because it is lying on the opposite direction of my weight vector. Okay, so I hope there was no doubt in this question. Okay, this type of question. A hard margin SVM is trained on a linearly separable data set with a positive margin. The features are in R2. Optimal vector given is 3, 4. Find the distance between the two supporting hyperplane. So that is, you have to find this distance, the distance between the two supporting hyperplane. What is the formula for finding the distance between two supporting hyperplane?
Norm of W divided by 2.
Just opposite of that.
Distance between the 2 points.
Not the distance between the 2 points. I am asking the distance between two supporting hyperplane. Yeah, 2 by norm of W is correct one. Okay, it is given by 2 by norm of W. Okay, if you want to know how, I will quickly tell. Let's suppose this is your line W transpose X equal to 0. Okay, this is my weight vector. Okay, then you have this margin line. Okay, that is the line W transpose X equal to 1. Okay, now how you define the margin is you will choose a data point which is closest to my decision boundary. Okay, so the closest point defines the margin, right? because they has to lie on the supporting hyperplane. Okay. So what you can do is you can project your this data point onto the weight vector. Okay. So let's suppose this is my weight vector. This is my data point. I will project it on here, and then I will calculate the norm of this projected data point, because the norm would be the distance here. Correct? So first of all, is the idea clear to everyone?
Yes, sir.
Okay. So if assuming that this is my data point X, then how I'm going to find the projection? What was the formula for projection? We discussed it in the starting at the PCA. If I want to project
Yeah, W transpose.
W transpose X
into W
Okay.
into W. Now here there was no guarantee
for,
that W would be unit vector, so
for norm of W.
not norm of W, it will be W transpose W. Okay. So this will be the projected vector. So once you got the projected vector, what you need to calculate is this distance. So that's basically the norm square of this. Okay. So if I go ahead and calculate the norm square of W transpose X into W by W transpose W, I will going to calculate this value. Okay. I hope it is clear. Okay. So
Sir,
it will become W
um,
trans. Yeah.
I don't understand why we are doing this. Can you please explain again?
Yeah. Yeah. Sure. So what we need to find here was the distance between the supporting hyperplane. Okay. So I was just explaining how the distance comes. Okay. So we have this decision boundary W transpose X equal to 0. Okay. We have this margin line W transpose X equal to 1. Okay. And there's some data point that is lying on this margin line. Okay. The distance that we need is this distance, what it should be. Okay. How we can find the distance is I can project this data point X onto my weight vector, and wherever that projected data point comes, I can take the norm of that. Okay, because the norm would be the distance from the origin. So thus that will give me the required distance between this linear decision boundary and the margin. Okay.
Okay, sir.
Is it okay? So then we go with the projection, that the projection of X onto W is W transpose X by W transpose W into W. If I go with the norm square formula, okay, that is just this projected data point transpose the projected data point. Okay. So it will become W transpose X, W transpose X into uh, W. Okay. This here it will become flip, and this transpose will come on this. So W transpose, then W transpose X, and this part will remain as it is. Okay. The below part will just become the W transpose W into W transpose W. Okay. So it will basically become W transpose W square. Okay. Now because these two are the scalar quantity, okay, and they will be the same. So again, it will be the square of this. So I can write it as W transpose X square divided by W transpose W square. This will cancel out this part. And once you take the square root, what you will left with W transpose X, and the square root of W transpose W is basically the norm of W. Okay. And because the W transpose X value here, it was 1. So it will comes out 1 upon norm of W. Okay. This was the distance from one side of margin. If you consider it from the other side also, okay, that is we only considered this side. If you consider this side also, this will also comes out to be 1 by norm of W. if you add these two, that you will get the total distance between the two supporting hyperplane, 1 by norm of W plus 1 by norm of W, 2 by norm of W. So is it clear how the distance would be 2 by norm of W between the two supporting hyperplanes?
Yes,
I
sir.
might have gone a little bit fast on this derivation, so but I don't think so it will be much useful from the exam point of view. Even if you remember just the final formula, that it would be the 2 by norm of W. That would also suffice. Okay.
Sir, again, just the norm of W. Can you just tell what should I be remembering when I do that norm of W? Only that part I'm still
It
like.
would be the square root of 3 square plus 4 square. So here the W is 3 by 4, 3 comma 4. Okay, so
Okay.
it will be the square root of 3 square plus 4 square. In general, it's like W1 square plus W2 square. That, that is the norm of W.
Okay, sir. Understood.
Okay. Any more doubt in this question? Okay. Very good.
No, sir.
So, so the first part we have already solved for the next question, the perfectron one. Okay. This is the second part. That in the case of hard margin SVM, if alpha star I is greater than equal to 0, the point xi is a support vector. Is it correct? Will it be true or false?
Yeah,
False.
correct.
True. Sir,
Okay.
true, right?
So
It should be true.
again, revise the what was the condition for a support vector? Alpha star I should be
Alpha.
strictly greater than 0.
Yes.
Okay. But
Acha.
here they are telling that it is greater than equal to 0. Okay. Once the equality comes, it will not be the support vector. So this would be false. Okay.
Yes, sir.
Okay. The next question was on soft margin SVM. So let's first revise the soft margin SVM part and the week 11. Week 11. So soft margin SVM is an extended version of the hard margin SVM. To implement this algorithm onto the dataset, which is not linearly separable. The main funda behind the soft margin SVM is we assume that our data point, which are not linearly separable. So again, we have this line, then we have some margin. Previously, we had a fully separated data points, that is all the red one on one side, all the green one were on the other side. But now we can have the condition that one green data point can lie here, one green data point can lie here, it can even lie here, that is between the margin and the decision boundary. Same goes for the red one. Red one can lie here, it can lie here, it can lie here. Okay. So these fixed data points that I created here are 5. Okay. We assume that all these data points, which does not follow this our criteria of linearly separability with some positive margin, are going to pay some kind of bribe or some kind of penalty to go to the correct side of the margin. So for example, this data point supposed to be on this side. So it will pay some kind of bribe to go on to that side. Similarly, this data point also has to pay some kind of bribe to go to this beyond the margin. Yes. Okay. Similarly for this, and all these 5 data points. These 5 data points. Okay. And that bribe is denoted by the term psi I. Okay. That is nothing but the max of 0 comma 1 minus W transpose Xi Yi. Okay. How does this make sense? That if the point is already on the correct side of the margin, then for that, this W transpose Xi Yi value would be greater than 1. Okay. So in that case, we do not want this data point to pay any bribe. So that's why the 1 minus 1, 1 minus something greater than 1 would be negative. So it will won't pay any kind of bribe. But for any point which is violating the margin, it will have the W transpose Xi Yi value to be less than 1. Because if it is like somewhere here, so let's say this is the line where W transpose Xi value is 0.5. Okay. Then the amount of bribe it will pay is 1 minus 0.5, that is 0.5. Okay. So yeah, if let's suppose one of my green data point is lying on this margin line, that is the line of W transpose Xi equal to -1. Then can you tell how much bribe this green data point will pay to go on to the correct side?
Sorry,
2.
2.
2. Very good. Because here it will satisfy the condition of W transpose Xi to be -1. So 1 minus 1 plus 2. So max of 0 comma 2 is 2. So it will pay 2 bribe, 2 amount of bribe to go on to the correct side. Okay. This was one notion of bribe. Yeah. Any doubt here?
So there were a few practice questions in previous year papers where we had to solve questions like this. So
Mm-hmm.
now, if it is on the hard on the boundary, then we would sorry, for every case we would just be using this formula and trying to find out what the solution would be, right?
Yeah.
Okay, irrespective of whether it is on the boundary or in one of the other side.
Yeah. You just fill what is the value of W transpose Xi Yi on that.
Okay, sir. Thank you.
Okay. So we have some question. Give me 1 minute, please. Hello everyone. So let's resume the class. Okay. Solve with us and PYQ will help. Okay. You can go through the solve with us slides and the PYQs for the last 2 or 3 terms. Okay. That will suffice, in my opinion. Yeah. So the bright part is complete. Now, what changes it will make in the original primal and the dual solution and the problem? Okay. So the changes it will make is previously we had this only norm w square plus we had this condition of alpha I times 1 minus w transpose xi yi. Okay. This was in the case of primal one, and in the dual one we just swept the max and min. Okay. So how does it go in the case of soft margin? Okay. So let's first write the objective function. Objective function was just our that we want to minimize this quantity norm w square by 2. Okay. Now we just does not want to minimize the norm. What we also want to do is we also want to minimize this not alpha I, our bribe that we are paying to each my data points. Okay. So this is something also that we want to minimize. And we are not just going to directly add the summation of the bribe. We are also going to give some penalty to that bribe with the regularization C. Okay. So that will be the objective function. My constraints are the same as before, that W transpose xi times yi are greater than equal to 1. All my bribes would be greater than equal to 0. Okay. So these will be the constraints. Okay. Now let's again only discuss the conclusion that we mainly get from this, especially about the support vector, how you identify it in terms of the soft margin case, because some things will change here. The main definition remains same, that for any ith data point, we check for the alpha I star value, and it has to be greater than equal to, greater than 0 for it to be classified as the support vector. Okay. But few of the condition will be remain same, that all the data points that lie on the supporting hyperplane, they need not to be the support vectors. Okay. And all the data points that does not lie on the supporting hyperplane, but also correctly lying on the correct side of the margin side. Okay. So that means all these green data points which are lying on the correct side of the supporting hyperplane. Okay. And beyond the margin, all these red data point which are lying on the correct side of the supporting hyperplane and beyond the margin. Okay. These will not be support vectors. Okay. Support vectors will be the data points which are lying on the support hyperplane, plus here all the data points which are violating the constraint of the separability and the margin will also be included in the support vectors. That is this data point, this data point. Okay. All these 7 data points will also be the support vectors. Okay. That is, this data point is what? It is violating the margin constraint, that all the data points satisfy that W transpose xi yi is greater than equal to 1. It is violating that part. It is not violating the constraint of my whether the data point, all the positive data points lie on this side, but it is violating the margin constraint. This data point violating the constraint of the separability, that negative data points lie on this side. Okay. So all these 2 types of constraints are there. One is it is violating the margin, like here. One is it is lying on the opposite side of my decision boundary, like this. Okay, these. And these are again the lying on the different side of the decision boundary, while these 2 data points are violating the margin constraint. So these 2 type of constraints data point are definitely support vectors. Okay, they will always be included as a support vectors. Plus, there's one more speciality in these data points, that the value of alpha I for all of these data points will be equal to C. Okay, for all the data points which violates the margin, which lie in opposite side of the decision boundary, okay, will have the alpha star I value to be C, and because C would be greater than equal to 0, okay, these data point will also classify as a support vector. Are the condition clear? All support uh, uh, data points which lies on correct side of decision boundary and does not violate margin. Okay, they are not support vectors. Okay. Data points which lies on supporting hyperplane may or may not be a support vector. Let me write it in short form SV. Okay. Third one that I discussed, that all the points which violates the margin or misclassified. Okay, misclassified means lying in the opposite direction of decision boundary. Okay, they are support vector with alpha I star value to be equal to C. C was this regularization that we introduced. Okay, so these observation about the support vector, they are very important. Okay, even if you forget that, you can go through this video again, or you can go to MLT FAQ site. Okay, mlt-faq.verfel.app. In that, in the week 11, in the support vector, I have also mentioned these final forms. Okay, so is this clear to everyone? These points?
Yes, sir.
Yeah. So this was about the. We had one more thing, bagging, boosting, and. Okay. So before the bagging boosting, let's discuss the bias and variance. So what is bias? What is variance? So variance
We
means, yeah, yes, go ahead. Do you want to say something? Okay. So the variance means uh, prediction that we are making on our data points. Okay. What is the variance among that? Okay. What is the spread among the prediction? If I make any fluctuation in my data point position, okay, if I change the position of my data point a little bit, then how much fluctuation in the prediction it will make, my model will make. How much fluctuation in terms of prediction my model will make. Okay, that's the variance. Okay, bias, on the other hand, is on an average. If you are training different models on different subset of a data, okay, by using, let's say, the cross validation, if you are training a on different subset of the data, then you will be getting different kind of prediction. Okay, so on an average, the prediction if I take, then how far it is from my true prediction. That is the bias. So bias basically tells you on an average how your model performs. Okay. And variance is basically the spread in the prediction, or basically if I make any kind of fluctuation in my position of my data points, how fluctuation will happen in the how much fluctuation it will happen in the prediction of my data point also. Okay.
Sir, can you
Now,
tell once again this bias?
yeah, bias is on an average how my model is performing. So let's suppose if I have a data set and I make some subset of the data set. Okay. So I have this data set D, which contains my x1 till xn, and I am making subset from this original data set, and I'm training models on those subsets, and I will get different kind of predictions. And if I take the average prediction for one data point, okay, then how far that average prediction is from the true prediction. Basically, the subtract of the average prediction with respect to the true label. Okay, don't worry, don't ask the question of calculating the bias and variance. Okay, so just remember that bias is basically on an average how your model performs. Variance is the fluctuation in the prediction that will happen if I like make any changes in the position of a data point. Okay. Now, with respect to bias and variance, generally the question that is asked is, yeah, yes.
Sir, continue.
With respect to bias and variance, the question is generally asked is in terms of overfitting and underfitting. Okay. You have to tell us about the whether the bias will be high or the variance will be high. So tell me about the case of underfitting. Bias will be high or low?
Hi.
Okay, high. What about variance?
No.
Low. For the overfitting case,
Bias low and
bias
variance
would be
high.
bias low, variance high. Very good. Okay. So overfitting, that is if you have a complex model, variance would be high for that model. What is it in my underfitting? It performed poorly on both training and the test. Overfitting, it performed very well on the training, but poorly on test. Yeah. So that concludes the bias variance part. Now comes the ensemble method. Okay. So ensemble, can anybody tell what does it, what does you guys understand from the ensemble methods?
Yeah, ensemble method aggregation. I have
Yeah.
heard this.
Correct. So that was like a very good one answer, one word answer, that it's the aggregation. Okay. Instead of just using one model for the prediction, we take multiple models prediction and combine their prediction power to make the final decision. That's what ensemble methods do. Okay. So it's a aggregation. So mainly with so three types. One was the bagging. So what happens in the bagging?
Yeah, in begging we can do a parallel, isn't it?
Yes, parallelization can be done in the bagging.
Yeah,
Uh,
and
So
one is
decision trees,
deep
decision
decision
trees
tree.
and parallel
yeah.
go together, right? Parallel
Yeah,
execution.
very good. So what how the bagging is done is we will have our entire data set, okay, and we will uniformly randomly sample from this data point for this data set with replacement, and we will create some bags. Okay, so we'll be creating some different kind of bags, okay, each containing the same number of data point by randomly sampling with replacement from this original data set. And then on each of these bags, we will train the decision tree. Okay. Now, in general, if I talk about the bagging, you can train any other model also other than the decision tree. But in our course, we are following with the decision tree. So assume that what we are going to do follow. Okay. So we are going to train the models on each of these bags. Okay. And those trees that we are going to train, they will be deep trees. Okay. Overfitted tree technically, or the high variance trees. Okay. And then for the final prediction, we are going to take the majority of the prediction made by each of these trees. Okay, that's for the bagging too. And as you said, it can be done in parallel. Okay, once after you make the bag, you can do the parallel training of each of these trees. Okay, so any doubt in the bagging?
Sir, how exactly do we choose on what decision stumps do we choose the bagging? Like, how do we
Uh,
make sure we separate it properly, or does it not matter because we have to go through everything?
Separate from. I did not get your question. Can you please repeat?
Sir,
How
I'll tell it at the end of the session once we complete. I don't want to hold on
okay,
to it.
sure, sure. So go with the second part, that is the random forest. Random forest is quite similar to the bagging in most of the process. Okay, that is you will have your original data set. You will again going to randomly sample with replacement from this data set, and you will make some bags, and you are going to train on each of these bags. And for the final prediction, you are again going to take the majority vote for each of these prediction. Again, it can be done in parallel. All of things are same. Only thing is different is the number of features that you are going to take while training each of these decision tree for each of the split in that each of these decision tree. Okay. In bagging, we are going to take all the features in training of any decision tree in those bags. In the random forest, to make sure that the models that we are going to get here remains uncorrelated to each other. While splitting any node in each of these decision tree, we take a random subset of the feature. At every split, at every node, at every decision tree, we take a random subset of the features. And that will make sure that each of these tree will be grown independent to each other. Okay, that's the only difference, that you take a random subset of the features. Okay, if the question asks why it was done, to make the trees uncorrelated. Okay, so any doubt here? Okay,
No, sir.
now the last portion of the week 11 is the boosting. And boosting, there are different methods: ADA boost, Cata boost, XZ boost, but the only method that we saw in our course is ADA boost. Okay, so what happens in the ADA boost? Please repeat random forest. Okay, yeah, so random forest, as I said, it is similar to what process happen in the bagging. The only thing that it will make a difference is first you will make the different bags from your original data set by randomly sampling with replacement. But while training the tree on each of these bags, okay, you are going to ask some question to split the node, right? So while making any split, instead of taking all the features, you will take a random subset of the features to make the split. Okay, that's the main difference. And why it was done? So that each of the tree here, as it will be grown by taking a random subset every time for every split, they will grow independent to each other. And thus, the tree that you will get in the random forest will be uncorrelated. That helps us reducing the variance in the final prediction. Okay. Now comes the ADA boost. So what can you tell me about the ADA boost?
Start by initializing the weight to 1 by n for all the
Very
data
good.
points.
Yes.
Compute the weight.
Hmm. So I
And
will
see
explain the
if
ADA boost. Yeah.
predicted is not equal to the actual value, then we update the weight.
Very good. And even if like it is equal, don't we update the weight in that case also?
No, in that case, we don't update.
We update it, but we update it differently, right?
Okay. Yeah.
So I will go through these notes to explain it because it has some mathematical notations more. Okay. So if I talk about the process first, what AdaBoost does is we will initialize the weights as you said, and the first initialization is done uniformly. That each of the weight for my data point will be given equal weightage, that is 1 by n, uniform weightage. Then we will run the algorithm for some number of iteration. Okay. And we will train a weak classifier. Weak classifier can be a decision stump in which you are just making a one split. Okay. So those are called the decision stump in which we are only making only one split. Okay. So those are called the weak learners. Weak learners are those which perform slightly better than a random guess. Okay. So you are going to train some weak learner, a weak decision stump you are going to train. And now that tree will going to make some kind of error. So you are going to store the error as the weightage that you have given to each my data set. Okay. Times whether this was an error or not. Okay. So initially, if all the data points has the weightage as 1 by n, it will be just simply the fraction of the data point which got misclassified. Okay. Initial for the initial part, but for the later iteration, it will change. Okay. But most likely they do not go till that complexity. So you can, for the simplification, you can just remember that error here is just a fraction of the data point which are misclassified. So if out of 10, 4 data points are misclassified, it would be 4 by 10. Okay. Then you compute the model weight that is given by as alpha. That is nothing but half ln 1 minus the error term divided by the error term. So if I got the error as let's say 4 by 10, it would be half ln. Ln is this the natural log 1 minus 4 by 10 divided by the 4 by 10. So 6 by 4. Okay, half ln of that, whatever value got is the alpha t. T here denotes the number of iteration for which you are running. Okay, this alpha will be useful at the time of prediction. Then we update the data points weight. Okay, but there are updates in two ways. For the data point which are misclassified, we will increase their weightage. Okay, and how we are going to increase it? It's e power alpha t. Alpha, whatever alpha you got, you will make an e power of that. Okay, and multiply it with the previous weight. So here initially that weight is 1 by n. So 1 by n will be multiplied with e power alpha if my current data point is misclassified. If it is correctly classified, we reduce its weight by e power negative alpha. Okay. And to make it follow a probability distribution, we normalize this. Okay. That's basically the weightage for each data point divided by the summation of weightage for all of the data points so that it behaves like a probability distribution. Now this entire process from here till here will continue for some number of iteration. And then for the final prediction, we call it as sine of summation from I equal to 1 to t, the number of iteration for which you have trained it, alpha t ht. ht we were denoting as the decision tree that I am training. Okay. So in the first one, the first decision tree is h1, then the second iteration I train the tree h2, like that. And the alpha t. Okay. The model weight that I got from here, the half ln thing. Okay. So this is how you do the boosting. Okay. Now, main observation that here was boosting train the model sequentially. Unlike bagging, which can be done parallel, it needs to be done in sequential. Okay. It focus on the mistakes which are done by the previous model, and we try to weight those data points, okay, which are previously misclassified with my model and increase their weight. So we are basically focusing on those data point more which are getting misclassified, while we will focus less on those data points which are getting correctly classified already. Okay, so it focus more on the uh, misclassified data points rather than the already correctly classified data points. So it's try to correct the previous mistakes in each iteration. Okay, the other points are not very much useful for you. Okay, main was this only that it can be done in sequential. Second thing, uh, it tried to correct the mistake of previous models that it has trained. Okay, that can be inferred from this weightage update rule also. Okay, for the misclassified, we give more weightage. For the correctly classified, we reduce their weightage. Yeah, so is boosting clear? Okay,
Yes, sir.
very good. Okay, then let's come back to these questions. Based on the above data, answer the given sub question. Consider a soft margin case, okay, with P to be 3 that has been trained on a data set with feature in R2. The decision boundary and the supporting hyperplanes are displayed below. 4 points from the training data points are also displayed. Okay, so these 4 points. Okay, green data points belongs to class 1, red data point belongs to class -1. Symbols psi and the alpha have their usual meaning. Assume that W, psi I, and alpha I represents the optimal values. Then, what is the value of psi 1, psi 2, psi 3, and alpha 1, alpha 3, alpha 4? Okay, so first of all, tell me what will be the value of psi 1? For this data point, what will be the value of psi 1? Yes,
Um, 2, right?
2, correct. Okay, as it is lying on this hyperplane, which is W transpose X equal to -1. Okay, so if you recall the formula, max of 0, 1 minus W transpose Xi times Yi. Okay, Yi for this data point is 1. W transpose Xi value is -1. So 1 minus -1 is 2. So psi 1 value would be 2. Very good. What about which is psi 2? Where is psi 2? Psi 2 is here.
0. Sorry, 1.
1. Very good. Okay, because it is W transpose X equal to 0.
Yes, sir.
Okay, so this value would be 0. So max of 0, 1. So psi 2 would be 1. What about psi 3? It is a
0.
W transpose 4. Very good. It will be 0. Okay. Now comes the alpha part. Okay. For the alpha, assume that if you think that you will not be able to find the alpha value, then answer would be -1. Okay. That's what mentioned in the question or in the original question. I just forgot to add that. So first tell me the alpha 1. Where is alpha 1? Alpha 1 is here. What do you think will be the value of alpha 1? Can you find the alpha 1 here?
Yes.
What would be it would be?
So it would be 3, right?
Very good. Why?
So because WTX IYI is lesser than 1,
Hmm.
and if that is the case, then alpha I is equal to C, and in the question it's been mentioned C is equal to 3.
Very good. Very good. Okay. So that's why alpha 1 to be C. Okay. These are among those data points which either violates the margin or lying on the opposite side of the decision boundary. Now what about alpha 3? Alpha 3 is this. What would be its value?
0.
0.
Very good. Alpha 3 would be 0 because it is lying on the correct side of the margin and also on the decision boundary, and it's lying beyond the margin, so it does not pay any bribe. It does not lying on the supporting hyperplane. So of course it is not at all important for creating the supporting hyperplane and the supporting boundary. So of course its alpha value would be 0. What about alpha 4? Where is alpha 4? Alpha 4 is here. Can you tell what will be the value of alpha 4 exactly? If you cannot tell, then the answer would be -1.
Sir, I'm not sure.
Yeah, it will be no.
Right? We cannot tell, right? Because it is lying on the supporting hyperplane. So its value can be anything greater than equal to 0, right?
Yes, sir.
Yes, sir.
So for the alpha 4, you in the original question it was written that if you cannot find the alpha, then put the answer is -1. So for this one, it would be -1. Okay, it's not the alpha value, but it's just that the placeholder for the answer. Okay. So any doubt in these type of questions?
No, sir.
Now, okay, this was a very simple one. Match the characteristic given below. So one is the decision stump, deep decision
Option.
tree.
Option A.
Option. Very good. Bagging needs deep decision tree and they can be done in parallel. Boosting needs decision stumps and they need sequential execution. So boosting is 1 4 4. I hope there's no doubt in this question. Okay. Now this question, which is related to a little bit from the regularization point of view, which includes in week 6, but also it includes the factor of whether you are able to understand how the regularization controls the overfitting and underfitting case and how the law of pension get affected. So consider a regression problem that has a training and the test data. Ridge regression is applied on the problem for various values of lambda. The training and the test dataset then plotted against some function of lambda. Okay, so this is some function of lambda, not the direct lambda. Remember, which we call as f of lambda. Not that the continuous curves are obtained by connecting the data points using a smooth curve. What is the most appropriate choice of f of lambda? Recall that the regularized loss is the sum of SSC plus the regularization term. SSC is the sum of squared error. So from the given graph, first of all, tell me what do you infer? Okay, tell me what is happening if my f of x, but not f of x, f of lambda is increasing with respect to the training loss and the test loss. If my f of lambda increases, then my training loss,
Decreases.
yeah. If f of lambda increases, training loss decreases. What about test one?
Test increases.
It increases. Okay. In the scenario of this, train is less, test is very high. What type of thing happen?
Overfitting.
Very good. So f of lambda is something that if you increases, your model overfit. Okay. Now, in terms of ridge regularization, when it happens that your model overfit, like when you choose lambda to be very low value or when you choose lambda to be high value.
So it overfits when you choose lambda to be low, right?
Very good. Okay. So when lambda is low, then in the ridge regression, your model overfit. Okay. Now compare these two. What can you tell? What is the relationship between lambda and f of lambda?
Inversely proportional.
Inversely proportional. So among the option, which one is the correct?
A.
A. Okay. So that's how you can solve this question. Focus on the graph, what is happening with respect to your function of lambda and the training and the test loss, and then infer the result from that. Compare it with what happens generally, and then you will be able to get the answer. So anybody has any doubt in this question?
Sir, if it was changed, if as in if the value of f lambda is increasing and the training is also increasing, but the testing is decreasing, then the model is underfitting, right?
No. In the underfitting case, both training and the test will increase. That is the case when
Oh,
f of
okay.
lambda increases.
Okay, sir. Okay.
So in that case also you can try and you will get the same result, that it will go in the opposite direction.
Okay, sir.
Any more doubt? Okay. So yeah, week 12. So there are not many things in the week 12. First contains the summary of the loss functions and then the neural network part. So again, I will go to the website to summarize that because that has the visualization also. So will be much easy to you. So in the week 12, we try to basically make a summary of all the classification that models that we have seen and what are the different loss functions that we can make with respect to them. So one was the misclassification error, that is also known as the 0-1 loss. Okay, that's nothing but the number of data points which are misclassified divided by the n. Okay, the graphical representation for that is this. Okay, the second loss function that we saw was the squared loss, that is w transpose xi yi, that is my predicted value, minus 1. Sorry, minus. I think there is some mistake. No. One. Okay, okay. This was the simplified form that we got after going with, if you take it to be y, and then if you do the simplification, then this will be the final form that you will going to get. W transpose xi yi minus 1, the whole square. Okay. So that was the squared loss. Okay. Then comes the hinge loss. Okay. That is related to your SVM. If you see the form, it's similar to what I wrote down for the epsilon term. Okay. Max of 0, 1 minus W transpose xi yi. Geometrically, it looked like this. Okay. One line this, and then it will be 0 after the 1. Then comes the logistic loss, which is the natural log of 1 plus e power negative W transpose x y. Okay. So which is a smooth curve. Okay, it's a smoother version of the hinge laws, like this. Then the final one is the perceptron laws, that is max of 0, negative W transpose Xi by I. In the hinge laws, we have 1 minus W transpose Xy. In the perceptron, it's just negative of W transpose Xy. And that's why it starts from 0. Okay. While the hinge laws, it is touching at 1. Okay. So these are the laws mentioned. You have to memorize this formula and their graphical representation. Okay. Now comes the neural network architecture. Okay. In our course of MLT, we have just seen it from the broader point of view. Okay. So just understand their architecture and specifically the activation function part and how you do the feed forward propagation. Okay. So what will happen in the neural network, that you will be having 3 different kind of layer. One is called the input layer, one is called as the hidden layer, one is called as the output layer. As the name suggests, output layer will give you the output. Input layer will be your data points, which will take the input. Hidden layer is something that we will be hidden from the model point of view. Okay, and that will do the initial internal computation to predict the final output. Okay, for any neural network architecture, in the simpler case that we are taking in our course, there would be only one input layer and one output layer, but there can be more than one hidden layer. Okay. Now, the number of neurons in the input layer is same as the number of dimension in which your data points lie. So if my data points lie in R3, I will have three neurons. If it lie in R10, then I will have 10 neurons. Okay. The number of neurons in the hidden layer are the hyperparameters. The number of hidden layers itself is the hyperparameter. So you can chase as many hidden layers you want and as many neurons you want in your any hidden layer. Okay. There's no guarantee that the number of neurons in the hidden layer should be same. So like even though like in this picture, both hidden layers contains only 4 neurons, but it can also happen like this hidden layer contains 4, this contains 3. That can also suffice. Okay. For the output layers, it depends upon the problem. If you are solving a regression problem, it will only contain 1 neuron. Okay, that is your final prediction. If you are solving a binary classification, then also it will only contain 1 neuron. But if you are going to solve a multi-class classification problem, then it will contain more than 1 neuron, and the number of neuron in that case will be equal to the number of class that you have. So if I have a 5 class classification problem, then I will have 5 neurons in the output layer. Okay. So first of all, is the architecture clear?
Yes, sir.
Now, one simpler type of question that is generally asked is the parameters. How many parameters will be there? So, okay, this one, no, I have to move to front. That's not opening. Oh, sorry. Stop share. So let's keep this as 3. Keep this as 4. Again 3, and this is 1. Okay. So I hope you guys are able to see this. It's a simpler neural architecture. Okay, so each let me shape FATH with okay, yeah. So each neuron will be connected to the neuron, okay, in the next layer. So like this neuron will be connected to this neuron also, and this neuron will be connected to this neuron also. This will be connected to this one, and this will be connected to this one also. Okay. Similarly goes for the second and the third one also. Okay. So this is called as the dense connection. Okay, where each neuron will be connecting to every other neuron in the next layer. Okay, and for each of these connections, okay, there will be one weight parameter associated with it. Okay, so if I have three neurons in the hidden layer, four neurons in the three neurons in the input layer, four neurons in the first hidden layer, then how many parameter will be there in between? Just the weight one. How many weight parameter will be there? As each of these neuron will be connected to every other neuron in the next layer, and they very good, 12. Okay, so each connection will contain one weight. So if I have three neurons in the input, four in the hidden layer, okay, so there will be total 12 connection because one connects with four. Okay, so if I have three will connect with all of these four, so it will be 12, 3 into 4. Okay, so it will be a total 12 parameter connection. Okay, what about between these two? It
So
will be
12
again
again.
12 again. What about the second
3.
hidden layer and the output? 3. Okay, so these are the number of total weights. 12 plus 12 plus 3. Okay, 27. These are the number of weights. Okay, and a common mistake that a student does generally at this point is they will multiply the neurons consecutively, like 3 into 4 into 3 into 1. Okay, it should not be like this. It be 3 into 4 plus 4 into 3 plus 3 into 1. That's the total number of weights. Okay, now for that bias. Okay, bias is added. Uh, Bias does not get added in the input layer, except the input layer it is getting added in each of the neuron, whether it is the hidden layer or the output layer. Okay, so as there are four neurons in this hidden layer, there will be four bias associated with each neuron. So four bias from here, three from here, one from here. Total 8 bias, 27 weights, 8 bias, total 35 parameters. Okay, this is how you can calculate the number of parameters.
So could you explain this again once?
Yeah, bias partner.
Yeah.
Okay, so input layer does not have any bias.
Okay.
Okay, first thing, only the hidden layers will have, or the output layer will have. Okay, and bias is associated with each neuron. Okay, so as there are four neurons in this hidden layer, there will be four bias.
Okay.
Three from here again, one from here.
So 7.
8.
Sorry. Yeah. 8.
8. Okay, 8 bias and 27 weights we got. Okay, so 27 plus 8 bias, total 35 parameters. Okay.
Okay, sir. Got it. Yes.
So this is how you calculate the total number of parameters. Just focus on what the question is asking, whether they are asking you to include the bias or not. Okay. So Mr. Net answer. Yeah. So that was the structure part. Let's again back here. Okay. So now comes the most important part, that is the activation function. Okay. Why activation functions are important? Because if we do not use the activation function, the neural network structure will be same as a simple linear regression model. Because if you see, sorry, yeah, because if you see, what we are doing is just a multiplication between the data point and the weight parameters. Okay, and if you continuously doing this, this will be same as the linear regression model. Okay, so we want to introduce non-linearity here, and for that we introduce the activation function. And our course, only the two activation functions are more useful. One is the ReLU, which is the max of 0, x. For any input, if you are going to give to the ReLU, it will be max of 0, x. If x is greater than 0, it will remain as it is. Less than 0, it will become 0. Its graphical representation is something this. Okay. The another activation function is the sigmoid one that we saw in the logistic regression. 1 upon 1 plus e power negative z. Okay. So yeah, that's all. Now let me open one more thing here. That concludes the forward pass. So with that, we will conclude the syllabus.
Sir, could you, by any chance, could you please give us a question?
Yeah, that's what I'm using.
Okay, sir, fine.
I think one was given with week 12 all with the slides. Yeah. Okay. So okay, so it was one diagram in which our input was in R3. We had two hidden layers, okay, each containing 3 and 3 neurons, and one output layer. Okay. Now, even though the question was just asking for the final case here, but I hope you will be able to get the how the feed forward works with respect to this. Okay. So the question says that let the output of the second hidden layer after applying the activation function is this. Okay. Then find the cross entropy loss if this is the weight of the ith element and 1 is the bias. Okay. So these are the weights. This is the bias that we are adding. Okay. So how you're going to do is we'll take this output of the second hidden layer that we got. Okay. We'll multiply them with the weights that it has. Okay. Correspondingly, you will get one output. And because in the question, I think it was mentioned that we use the sigmoid activation function. For the output of this linear combination, we feed it into the sigmoid function and we got this probability. That was the probability for the binary classification problem. Okay. But same thing is happening with respect to each of this pass through here. That you will initialize your, sorry, not the initialize of weight vector. You will have your data points. Then you will have certain weights associated with it. So one more question if I take, I think it was in last term QP. Hmm. Okay. So here also was one question that they have given these weights, okay, and the output weight also. So if I read the question, consider a single layer neural network comprising two neurons in the hidden layer. The parameters are given below. So W11, W21 is half, W21 and W22 is 1 and minus 1, and W out is 2 and minus 2, where Wji represents the weight associated with the jth neuron for the ith data point. Okay. Suppose we are solving this problem. So uh, let me write it in the notepad and then I will. Okay. Yeah. So let me share my screen from notepad. Is my screen visible? Okay, I hope it is. So what they were telling us, they have given us this W11, which is 1 by 2, W12, which is also 1 by 2. Okay, and we also had the W21, which was 1, W2, 2, which is -1. Okay, on how this indexing work, this is some J, okay, which represents the neuron. This represents the data point or the feature index. Okay, so if this is my x1, this is my x2. Okay, this 1 and 2 here denotes the x1, x2 value. Okay, sorry, this should be here W2, and this should be here W2, W2. Yeah, now it's correct. Okay, so this subscript part, okay, that's the feature value here. Okay, while this superscript part, okay, this denotes the neuron in the next layer. So 1 here means these are the parameter associated in this connection. Okay, so this is 1 by 2, this is 1 by 2. Okay, next if you see, these are okay, here it should be 1. Okay, so as the superscript is 2, that means these are denoting this connection. Okay, and 1 and 2, so that means this value is 1, this value is 2. Sorry, this value is -1. Okay, so even though like even if some different notation is used, they will explain how the notation is working. Okay, in this current notation setup, they have taken this superscript 1 to be the neuron and the subscript 1 to be the data point or the feature 1 index. Okay, so first of all, is this clear till now?
Yes, sir.
Okay, and the data point given to us is 1, 3. And also we have given this W out. Okay, so W out is 2, -2. So how the connection later will happen? This will go this. Okay, so 2, -2. Okay, okay, let's do the feed forward pass. 1, 3. So let's do this connection. What will be the output for this connection here? Choose the weights to be half and half. X is 1 by 3, 1 and 3. Okay, so you can multiply it like half and half here. Okay, so what it would be?
So 2.
2. Okay, so think of it connection is like this. Whatever the x1 feature is getting value, multiply it with the weight vector. Okay, similarly for this, multiply it with the weight vector, summation that. Okay, so that's 2. Okay, similarly now check for this connection. What you will get?
-2.
-2. Okay, now one more information was given in the question that the activation function that you are applying is ReLU. So on this output, you are going to apply the ReLU activation function. So what will be the value after applying ReLU on this? What it would be?
2.
2. What about on the this part?
0.
0. Okay. Now this output of the activation function is then fed into the next neuron parameter. Okay. So now tell me what value you will get after linear combination from here. Just like we did it here, try to follow it here also. What you will get? 4. Very good. Okay, this 2 into 2 plus this -2 into 0. So 4. Okay, then you will again apply ReLU on this 4. What you will get? 4 only because it's
4.
next of 0. So
Yes.
this is the final output for a feed-forward network. They're not going to ask more than this, except thing that they can change is the activation function. Instead of ReLU, they can use sigmoid or something. Okay, they can use different activation. Like in the hidden layer, they are using ReLU. In the output layer, they can use sigmoid also. That can also happen.
Um, Sir, I got all this. One small doubt, maybe I have missed it when you
Hmm.
told. When do we know when do we use ReLU and when do we use Sigmoid?
These are again the hyperparameters. More on this you will be learning in the deep learning course. Okay, this is
So,
just a basic level intro to the neural network. There's lot more to this which you will be learning in the DL in the DT.
sir, so if we get a question like this, then
No. We won't be asking question like this. Like which activation function should be used.
okay, all right, sir. Okay, thank you.
Yeah. So now let's solve some of the question that I had already from here. So basically, the first question is you have to identify which loss corresponds to which, like which curve here corresponds to which loss. So first one, that is this yellow. Which type of loss is this? The yellow one.
Squared.
Very good. What about green one? I hope the diagram was visible. This is the green one.
Perceptron, I think.
Hmm. Is it
Oh,
perceptron or
logistic. No, sorry, hinge.
very good? Hinge. Okay. A difference quite easy to remember is logistic will be a smooth one. Okay. Squared, of course, it is very easy to identify. Logistic will be the smoothest curve. Okay.
Three.
And among perceptron and the hinge, perceptron starts at 0, hinge starts at 1 or hit at 1. Okay. So now what about the third one?
Logistic.
Logistic.
Logistic. So fourth is perceptron.
Sir, could you just show the formula for the hinge loss?
Hinge loss, the formula was max of 0, 1 minus W transpose X, Y.
Okay, sir. Thank you.
For the perceptron, it's max of 0, negative W transpose X, Y. Okay. For the,
Here we don't have one minus, right? Because it
yeah, here
starts
we
at
don't
zero.
have the 1 minus.
Okay.
For, yeah, for the logistic, what was the formula? ln of 1 plus e power uh, W transpose X, Y. Okay. Squared, it's just W transpose X, Y minus 1, the whole square. The first question is done. The second one is the interesting one here, that which of the following statements are true? ln denotes the natural log. If you read through the option, can you tell what basically they are asking?
Basically, they're checking where if there is any point where any of the losses intersect each other.
Uh, Does they are asking for any of the laws or only specifically two laws?
Only logistic and hinge.
Hinge. Okay. So they are just asking for the hinge intersection point for hinge and logistic. So first from the graph, can you tell whether they intersect or not? The logistic and the hinge laws.
Logistic and hinge loss
Basically,
seem
green and red curve.
Yes, they do.
only after one.
After one or
Oh,
before one?
sorry.
Before one,
My
right?
bad, sir. Yeah.
Yeah, no problem.
Yes.
Okay, so they do intersect. So of course the second option is incorrect. Okay. Now, if you are going to solve this, you have to basically solve or equate these two function value. But one thing we know that it intersect after like before the zero. Oh, sorry, not the before the zero. Max of 0, 1 minus W transpose Xi. So they after 0 they intersect. Okay. So from the hinge formulation, okay, the value that you are going to get would be this value, 1 minus W transpose Xi by A, right? Because it's lying between 0 and 1. So at that point, the value of the hinge loss would be 1 minus W transpose Xy, right?
Yes, sir.
So W transpose Xy. For the logistic, we have this 1 plus e power negative W transpose Xy. To find the intersect, what you are going to do? You are going to equate these two and solve for the W transpose XY part. Can anybody tell me what it would be?
Um, Sir, I think it's
So for simplicity, we can do one thing that you can assume that W transpose X Y is Z. So what you have to solve is 1 minus Z equal to ln of 1 plus e power negative Z. Now start solving. So if you want to solve first, what you have to get rid of here? Um, see, Z, one Z is here, one Z is here. We have to, yeah, very good. We have to get rid of this ln, natural log here. How we can do that? Let's suppose if I had a square root in place of ln, then what I would have done to get rid of that?
so can't we exponentialize this
Yeah, that's the thing.
because it's the inverse of.
Yeah, that's what we are going to do. We basically do the inverse operation if we want to get rid of any operation. So if I want to get rid of logarithm, I will do the exponential here. So basically, I will take e power 1 minus z here. It would be e power ln of this. So this will just be e power negative z. Okay. Now, our simpler school thing that we do this, we are going to basically take our all the variable terms on one side. Okay. Now this quantity e power 1 minus z, can I write it as e power e divided by e power z?
Yes, sir.
Now this quantity when it will go, it will become e power negative z equal to 1. Again, this term, I can write it as 1 upon e power z.
Yes, sir.
What this would be?
Uh, so e power z is equal to e minus 1.
Hmm. Okay, e power z equal to e minus 1. Okay, till now.
Yes, sir.
Now, what is the thing that we want to get rid of? If I want z,
E
e, how I can get rid of?
replace the value. Sorry,
Replace the
log it.
log, natural log.
Yes, sir.
Ln of e power z equal to ln of e minus 1. This would be the z equal to uh, ln of e minus 1. My z was, where is my z? W transpose xy. So W transpose xy is ln of e minus 1. First option. Okay. So anybody has any doubt in this question? Okay. Is it clear for everyone, I hope? Next question is based on the neural network architecture. You have 5 neurons in the input layer, 10 and 10 neurons in the hidden layer 1 and hidden layer 2, and output layer contains 1 neuron. So how many learnable parameters are there, ignoring the bias?
Sir, it would be 50 plus 100 plus 10.
Plus 10. Okay, so 160. Very good. What is the most appropriate choice of the activation function for the output layer if the binary cross entropy loss is used? What it would be?
Sir, I don't know how do we do this. How do we choose this?
So when I was explaining the neural network architecture, I said one thing, yes, sigmoid is the correct answer, that for the output layer, if I have a binary classification problem, okay, then my output uh, activation function would be sigmoid. If I am having a regression problem, then my activation function would be linear. Linear means you are not going to do anything. It will be just the same output. Okay. If
Yes.
I am having a multi-class classification problem, then my output activation function would be softmax. There's something that you will study later, so you can forget that part of it. Okay.
Okay, sir.
But they are not going to ask what should be the appropriate activation function for the hidden layers. Okay. Just they can ask for the output. For linear, for the regression case, sigmoid, if you have a binary classification, softmax is multi-class classification. The last question for the day. For a particular data point, the activation after the first hidden layer in the forward pass is given to be this. What is the activation function used in this hidden layer? Is it ReLU, sigmoid?
Sir, it's relu.
Relu.
Okay, why it's not sigmoid?
Sir, sir, I did it's relu because the minimum value is 0. So what the function must have been is maximum of 0 or the other part. That is how I saw it.
Sigmoid is only between 0 and 1, so I can't. 1.2 is there, so 1.2 and 1.5
1.5,
both are there, so they
1.2.
can't.
Okay, so they can't be there. If it would have been a sigmoid. So that's okay. That was like more good reason.
Sir, if you don't mind my asking, like how much, like, do you have an idea of how many kind of questions are like these objective type questions and how many are actually numerical? Any idea in that?
No, not in that. I think nobody has any idea. So the
Acha, so I
inspector, how
can't,
many will that?
I can't
What I
just.
have is just what I know that there would be around 50% weightage for the last 4 weeks and 50%
Yes,
for the
yes,
first 8. That's all I know.
yes. Sir, I know you are taking the course for machine learning I mean techniques, but if similar things can be told for machine learning foundations also, if by chance, if you can, because I have both of them tomorrow.
For
You mean
this term,
Yes, sir. Actually, that's
no,
the
tomorrow
yes.
is the
Actually,
end term, right? For this term, it won't be possible. And if you have the course this term, then it will be very tricky, actually.
that's I should have realized that before. I thought I could handle it, but any just like I have done some questions on it, but like now I'm much more clarity at machine learning techniques, but in machine learning foundations I still a bit nervous, so that's why I was asking.
uh, well, MLF? I can only suggest that see the week 11 is just the stats 1, stats 2 part, right?
Yes,
So
sir. Yes.
I hope your stats was good. If
Hello.
your stat, yeah, hello, am I audible? Hello, am I audible?
Yeah, yeah, yeah. I can
Yeah,
hear you.
perfectly audible.
So if your stats is good, you can focus first on that part because some question generally comes from that. Like I think one was to find the like they will give a PDF generally, and you can ask for the value of k, something related to that, or some probability questions.
Okay,
Okay.
okay.
So one thing from there, one question surely practice from the KKT conditions, the current cross tucker part. Okay. We
Okay,
just
sir.
practice one or two and understand the all the current cross tucker condition, the
Sure.
stationary condition, complementary slackness, prime feasibility, dual feasibility. Okay.
Okay, sir.
So because most likely they will always ask one question from this, and
Okay, sir. Sure.
one question how you solve any optimization problem which is using Lagrangian or an unconstrained optimization.
Okay,
Okay.
sir. Sure. Sure, sir.
And go over the week 12 that have one part of like multivariate Gaussian. Okay. So how you if like two variables are following the Gaussian and if you do the summation of those two, then you will be getting a multivariate Gaussian distribution. So how you will find the mean for that and covariance matrix for that, that part
Sure.
also you can go.
Sure, sir.
So
Sure.
these will suffice. Now the rest depends upon how you studied for the quiz and quiz 2.
Yes,
The
yes.
last
I did study for quiz too, but I just a bit nervous.
and
Thank you, sir.
PC
Okay.
of course it's in there in MLT and ML. It's just the notations are different we are using. Otherwise, the base idea is same for PC.
Yes, sir. Yes, sir. Sure. Thank you so much, sir.
Sir, I have a question.
Yes.
Uh,
Yeah.
Sir, I'm not sure if you can, like, you have any idea about it, but I'm still going to ask in case, like, you can help us understand that from the week 1 to 8, what kind of questions can we generally expect? Because in quiz 1, quiz 2, from these weeks, we have solved both numerical and theoretical. So in the upcoming quiz, what is the general pattern like for like from week 1 to 8? Do we get like long 3 mark or 2 mark questions, or like 1 mark, maybe those kind of questions which are more theoretical based or something like that, which are like easy to just apply a formula and you get an answer. So from for week 1 to 8, what can we expect?
From week 1 to 8, the exact distribution of marks, I don't have any idea about the distribution, but about the type of questions, from week 4, the general type of pattern that they follow is like they can ask for any kind of like estimation question. From week
Mhm.
3, you can expect any kind of like numerical based question. That's the general pattern that they ask, in which they can ask you to perform k-means. From week 2, it is also more related to the theoretical part. Okay. From
Hmm.
week 1, you can expect a numerical kind of question. For week 5, both numerical and theoretical point of view, it's quite packed. Okay. They can ask you to
Hmm.
perform linear regression. They can ask some kind of like geometric view of linear regression, some kind of theoretical question related to SGD, like that. From week 6,
Hmm.
it's more packed with the theoretical question. So, but it can be clubbed with numerical if you include the cross validation, because from the I think last 2 terms, they are asking one question on cross validation. They will ask you to perform a cross validation, so you can expect that. From week 7, KNN, again, it's numerical. Decision tree is also numerical. Week 8, also it's more packed with the numerical, especially from the probability point of view. That's my idea.
Okay, sir.
Okay.
Sir, this PDF which you used to, take this session, can you please share this with us?
Okay, yeah. Give me 2 minutes.
So do we also have solutions in this PDF, like while you were like
No,
taking
this
this session?
like all the annotations that I did, only those things are there. There is
Okay.
something I explained verbally that is not written, then it won't be there.
Yeah. Okay.
Okay, guys, anyone else has any questions?
Sir, any final tips?
Okay, final tips for the anthem. Do not panic. Okay. Uh, Try to break down your problems that you have into smaller parts. Okay. If any graphical question is given, then analyze what things is happening geometrically and try to make sense from that. Okay. For the theoretical question, do read whether this condition will hold true in general scenario or not. Okay. Yeah,
I
that's
think
all
the
I have.
best tip I would give you guys is that rewatch the session, because see, Pulkit has covered everything from week 1 to 12. That is something that I have not seen in any session whatsoever. No TA till date has covered the entire session, the entire syllabus in one session. It's been what, 4.5 hours now at this point, and he has not just managed to squeeze 12 weeks in this session, but also the PYQ in this session. So hats off to Pulkit first of all.
Thank you.
I don't think anybody else could have managed it except for him. Um, he is of course the veteran TA. Kshitij, I guess you have a person to look up to when it comes to TA ship. So you got the perfect co-TA. So thank you, Pulkit. Thank you for taking this session, and it has been a wonderful session.
Thank
I
you.
swear, it has been a wonderful session, and I hope, guys, that you have found the session useful as well. And tomorrow, you guys ace your exam, because we tried to squeeze in everything that we could at the last moment. So I hope you found the session useful, and all the best all the very best for your end term tomorrow. And do let us know once you're done with your end term that whether we were able to help you out or not. You can mail us at our email IDs. We would love some feedback for the session and the other sessions as well that we have conducted till this point. So yeah, thank you guys. Thank you. Have a good night.
Thank you, sir.
Thank you,
Thank you
sir.
Thank
everyone for joining the
Yeah.
session and staying till the end. Good night, everyone, and all the best for your end term.
Good night.
Pulkit,
Thank you.
thank you so much. Thank you so much. That was a wonderful session, actually.
Thank you.
I must say, you have outdone yourself. You've outdone not just yourself, but the other TAs as well at this point.